Hello there and welcome. Tonight I want to take you somewhere, not to a place you can find on any map, but to a quiet space of wonder, a place we can visit together in the stillness of our minds. So find a comfortable position. Let your body feel heavy, supported and at ease. Allow the day to gently fade, its sounds and concerns drifting away like distant clouds. There is nothing to do right now, nothing to solve. There is only this moment, this quiet, and the journey we're about to begin. Breathe in, slowly, and as you breathe out, imagine you're releasing everything you no longer need to carry. Let your shoulders soften, let the muscles in your face relax. We are creating a space for peace, a sanctuary from the noise. Here, in this shared quiet, we can simply be. We can simply wonder. Tonight, our journey takes us into the vast, velvet darkness of space. But we are not looking for brilliant explosions or dramatic collisions. We are listening for a whisper, a faint, fleeting murmur from the deep. Imagine yourself looking up at a perfectly clear night sky, far from the glow of city lights. The stars are not just sharp points of light. They form a luminous tapestry, a glittering dust of diamonds scattered across an infinite black cloth. There is a profound silence here, a silence that is not empty but full of distance, full of time, and full of unanswered questions. It's in this deep, resonant quiet that our story begins. In the early days of 2023, astronomers, our patient watchers of the night, noticed something new. It wasn't a brilliant, blazing star. It was a faint smudge of light, a barely perceptible traveller moving through our solar system. Using a network of telescopes on Earth known as ATLAS, the Asteroid Terrestrial Impact Last Alert System, they logged this new guest. At first, it was given a designation that suggested it was from far, far away, from beyond our own sun's family. 3II Atlas. The I stood for interstellar, a visitor from another star system. The idea itself is a source of quiet wonder. A piece of another solar system wandering through the cosmic dark for millions, perhaps billions, of years, only to drift through our neighbourhood for a brief moment in time. A true ghost passing through. But as our watchers of the sky observed it more closely, the story shifted as stories in science so often do. The path it was taking, its trajectory through our system, began to look less like that of a transient visitor, and more like that of a resident, albeit one who had been away for a very, very long time. Its designation was gently changed. The I for interstellar was reconsidered, and it was reclassified as a long-period comet, a member of our own solar system, returning from the cold, distant edges. And then, just as we were getting to know it, it began to fade. The faint smudge of light, this whisper in the dark, started to unravel. It didn't explode in a fiery spectacle. It simply dissolved. It broke apart, its icy body fragmenting into a cloud of dust and gas, its substance returning to the quiet void from which it came. And just like that, it was gone. A fleeting guest who appeared for a moment and then vanished back into the silence. It's a story that could end right there. A minor astronomical event, a footnote in the celestial logs of a single year. A faint comet discovered, observed, and then gone. It's a question that, at first, seems to drift away just as the comet itself did, dissolving into the vastness of everything else we have to think about. But what if we hold on to it for a moment? What if we cup that question in our hands and look at it gently, in the soft light of contemplation? What if its disappearance wasn't an ending? What if it was simply a turn in a much, much longer path? This is the question that will guide our journey tonight. It's a question that acknowledges the scientific story, the observation, the data, the fragmentation, but then asks to look beyond it, into the realm of possibility. It's a question that builds a gentle intrigue, not with alarm, but with a sense of profound, quiet wonder. What if that visitor, 3I Atlas, was not just a random comet on a final self-destructive journey? What if its path was part of an ancient cosmic clockwork? What if its brief appearance was just one stop on a vast repeating orbit, a cycle that brings it back to the heart of our solar system, time and time again, across immense stretches of history? What if 3i Atlas, or the body from which it came, is a recurring visitor on a cycle of 12,000 years? Think about that for a moment. A 12,000-year orbit. An object that last visited our skies when our world was almost unrecognizably different. When mammoths still roamed parts of the Earth, and the last great ice age was just beginning to release its grip on the planet. An object that has been gone from our view for all of human recorded history, silently soaring out into the cold darkness, making a slow, graceful turn and beginning its long journey back. Its return in our time, then, would not be a random event. It would be an appointment, an ancient appointment, kept with silent gravitational precision. And its fragmentation, its gentle dissolving, might not be an end but a transformation, a shedding of a layer before the core of it, the heart of it, continues on its path to return once more another 12,000 years from now. This is not a theory we are setting out to prove. It is a thought we are setting out to explore, a possibility to meditate upon. It's a way of looking at the cosmos not just as a collection of objects and events, but as a story. A very, very long story. And we, in our brief moment, have just glimpsed one of its quietest, most mysterious characters. As we drift deeper into this idea, we might find that it connects us to something vast and beautiful. It connects our present moment to the deep past and the distant future. It makes the universe feel less like a chaotic, empty space, and more like a place of profound, underlying rhythm. A place of cycles, of returns, of quiet, patient journeys that unfold on a scale that humbles and inspires us. If you find comfort in these shared journeys into the cosmos, and if this sense of peaceful curiosity resonates with you, perhaps you might consider following along with more of these gentle explorations. There's something beautiful about building a quiet community of wanderers, all of us looking up at the same sky from our own peaceful corners of the world, sharing in these moments of cosmic contemplation as we drift towards sleep. Each night offers us a new mystery to ponder, a new question to hold gently in our minds as we rest. But for now, let that thought rest. Let's return to the image of that faint smudge of light. Don't try to see it with your eyes, see it with your mind. A wisp of ancient ice and dust, catching the faint light of our distant sun. It has travelled for thousands of years from the cold, dark edge of everything we know, a place of unimaginable quiet, a place where the sun is just another star in the sky. Imagine the beginning of its journey inward, a slight nudge, a gravitational whisper from a passing star perhaps, a tiny change in its path that, over millennia, guided it back toward us. Slowly, slowly, over thousands of years it fell toward the sun. It moved out of the great silent dark and into the realm of our solar system. It pierced the orbits of Neptune, Uranus, Saturn and Jupiter, those giant sleeping worlds. Its pace quickened, pulled by the sun's immense gravity. For 6,000 years, it fell inward, and for all that time, it was invisible to us. A ghost in the machine, a dark traveller on a dark road. It was only in the final months of its long approach that it came close enough to the sun for its ice to begin to warm. As it warmed, it released a cloud of gas and dust, the coma, a temporary atmosphere that is the signature of a comet. And it was this faint, glowing cloud that our telescopes finally saw, a whisper that had become just loud enough to hear. The astronomers who first spotted it were, in a way, like watchmen on a distant shore, finally seeing the faint light of a ship that had been at sea for longer than any ship in human history. They tracked its movement, calculated its speed, and tried to read its story from the light it gave off. They were deciphering a message written in physics, a message that had been in transit for millennia. They saw that it was moving fast, very fast. This was one of the clues that first pointed toward an interstellar origin. Objects that fall in from the farthest reaches of our own solar system are typically moving at a certain speed by the time they reach us. But this one seemed to be moving faster, as if it had an extra push. The kind of push it would have if it were just passing through from another star's domain. But the universe is a place of subtle complexities. Other factors can influence a comet's path. A gentle push of gas, venting from its surface as it heats up, can act like a tiny, unpredictable rocket engine, altering its course in ways that are difficult to model perfectly. And as more data came in, the picture became clearer. Its path was not a straight line passing through, but a very, very long and stretched out ellipse. An orbit, a closed loop. It was one of ours. It was coming home. And then came the final chapter of its visit. As it rounded the sun, at the closest point in its long journey, the thermal stress, the gravitational pull, became too much for its fragile icy structure. It had held together for thousands of years in the deep freeze of outer space. But here, in the warmth and light of the inner solar system, it began to surrender. Astronomers watched as the single point of light began to elongate, then to separate into distinct fragments. 4, then more. It was like watching a dandelion seed head finally yielding to a gentle breeze. Not a violent shattering, but a quiet, graceful dispersal. Each fragment, a miniature comet in its own right, continued along the same path, but as a looser, more diffuse cloud. The single whisper had become a chorus of even fainter whispers, each one fading until the entire presence was lost in the background glow of space. To our instruments, 3i Atlas ceased to exist. It was gone. But let us hold our gentle question again. What if this wasn't an end? In the quiet depths of space, nothing is ever truly lost. It only changes form. The dust and ice of that comet are still out there. They are now spread out along that same vast 12,000-year orbit. A ghostly trail of what once was. A breadcrumb trail marking a path through the cosmos. Perhaps the comet itself was just one piece of a much larger object that broke apart on a previous visit, 12,000 years ago. And perhaps on this visit, another piece broke away. The core of it, the largest and most resilient part, might still be out there, intact and unseen, continuing its silent journey back out into the cold. It has shed a part of itself, leaving a memory of its visit with us, before retreating into the darkness for another long, slow lap around its cosmic track. This is the beauty of thinking on these timescales. Our human lives are measured in decades, our civilizations in centuries or millennia. But the universe keeps a different kind of time. Its clocks tick in orbits that last for eons. Its events unfold with a patience that is almost impossible for us to fully grasp. To think about a 12,000-year cycle is to stretch our own sense of time. It is to connect with a rhythm that is so slow, so vast, that it feels eternal. It makes the frantic pace of our own world seem to slow down. It puts our worries and our deadlines into a new perspective. We are part of something so much older, so much slower, and so much more mysterious than our daily lives suggest. And so, as you lie here, breathing gently, let your mind drift with that idea. Let it float along that vast elliptical path. Travel outward from the sun, past the orbits of Mars, Jupiter, and Saturn. Feel the light and warmth of the sun fade behind you. Feel the silence deepen. Feel the cold return. You're moving through the quiet, empty spaces between the planets. The journey outward will take 6,000 years. Imagine the Earth, from this distance, shrinking to a bright blue-white star, and then fading into the general glimmer of the inner solar system. All of our history, all of our struggles and triumphs, unfolding on that tiny distant point of light as you drift silently onward. This is the journey the comet makes, a journey of immense solitude, a journey through a silence we can barely comprehend. And at the farthest point of its journey, it will slow and pause as if taking a breath, before the sun's faint but persistent gravity begins to pull it back again. The journey we're taking tonight is not one of facts and figures, but of feeling and wonder. It is an exercise in cosmic empathy, an attempt to feel the rhythm of a silent traveller, to imagine its long, lonely road, and to see our own world from its distant, silent perspective. Consider the nature of ice itself, the primary substance of our mysterious visitor. In the warmth of Earth, we know ice as something temporary, something that melts with the coming of spring, something that exists only in winter's embrace or in the artificial cold of our freezers. But in the deep spaces where comets dwell, ice is eternal. It is rock solid, harder than granite in those temperatures that hover just barely above absolute zero. Out there, in the Oort cloud, water ice mingles with frozen methane, frozen ammonia, frozen carbon dioxide, substances that on Earth we know only as gases or liquids, but which in that profound cold become the bedrock of these ancient travellers. This ice has been there since the very beginning, when our solar system was young, when the sun was just igniting its nuclear fires for the first time, when the planets were still accreting from clouds of dust and gas. This ice was forming in the cold outer reaches. It is primordial ice, older than the mountains, older than the oceans, older than life itself. It carries within its crystalline structure the memory of our solar system's birth. Every molecule locked in place for billions of years, waiting, just waiting. When we think about 3i Atlas, we're thinking about a messenger from that ancient time, a time capsule that has been circling in the dark, preserving its secrets in the deep freeze of space, and perhaps every 12,000 years it swings by to show us these secrets, to remind us of where we all came from. The dust that streams from a comet as it warms near the sun, that dust is stardust in the most literal sense. It is the processed material of stars that died before our sun was born, elements forged in stellar furnaces and scattered across the galaxy in supernova explosions, only to be gathered up again in the formation of new star systems like ours. The fragmentation we witnessed might be part of a natural process, a gradual unveiling that happens over many orbits. Each pass near the sun peels away another layer, like reading pages from an ancient book written in ice and stone. The comet grows smaller with each visit, but it also shares more of itself with the inner solar system. Some of that dust will drift through space for millions of years. Some of it will eventually spiral into the sun, and some of it, just a tiny fraction, will encounter Earth. Every year, our planet sweeps up about 40,000 tons of cosmic dust. Most of it comes from asteroids and comets, these visitors from the outer reaches of our solar system. It settles invisibly through our atmosphere, adding its ancient substance to our world. The dust from 3i Atlas is out there now, drifting on solar winds and radiation pressure, spreading through the inner solar system like a whispered secret being shared among the planets. Some of that dust may already be falling through our atmosphere, invisible to our eyes but present nonetheless. Ancient ice from the edge of everything becoming part of our world. Think about that for a moment. The rain that falls tomorrow might carry within it molecules that were locked in ice for 4.5 billion years. The water you drink might contain hydrogen atoms that have been circling in the dark since before Earth existed. We are, in the most profound sense, connected to these cosmic cycles. We are made of the same stuff, following the same physical laws, part of the same grand story. The instruments that detected 3i Atlas are marvels of human ingenuity, but they are also, in their way, quite humble. The Atlas system consists of 4 telescopes, each one relatively small by modern standards, scanning the sky methodically, night after night. They were designed primarily to watch for asteroids that might pose a threat to Earth, to give us warning of any cosmic debris on a collision course with our world. But in their patient watching, they also catch these other visitors, these gentle wanderers who pose no threat but offer us glimpses into the deeper mysteries of our cosmic neighbourhood. The telescopes work by taking multiple images of the same patch of sky, minutes apart, By comparing these images, astronomers can spot objects that move against the fixed background of stars. It's a simple principle, but it requires incredible precision and patience. Every night, these mechanical eyes capture thousands of images, each one examined by sophisticated software and, when something interesting appears, by human eyes as well. The discovery of 3-Eye Atlas was not a moment of dramatic revelation, but a gradual recognition, built up over multiple observations as its path and nature slowly became clear. The data from these observations is freely shared with astronomers around the world. Scientists in dozens of countries examined the light from 3-Eye Atlas, each one adding their own piece to the puzzle. Some measured its brightness, tracking how it changed over time. Others analyzed its spectrum, the specific wavelengths of light it reflected and emitted, looking for clues about its composition. Still others calculated and recalculated its orbit, trying to understand where it came from and where it was going. This collaborative effort, this pooling of human curiosity and expertise, is one of the beautiful aspects of astronomy. The sky belongs to everyone, and the mysteries it holds are puzzles for all of humanity to solve together. When 3-Eye Atlas appeared, it became a focal point for this collective wonder, this shared desire to understand our place in the cosmos. The fact that it fragmented and faded doesn't diminish the value of these observations. If anything, it makes them more precious. We caught a glimpse of something in transition, something in the very act of transformation. We witnessed a moment that will never repeat in exactly the same way. But perhaps it will repeat in a different way. Perhaps 12,000 years from now, another fragment of the same original body will make its way into the inner solar system. Perhaps it will be spotted by whatever incredible instruments humanity has developed by then. Or perhaps humanity itself will have changed so profoundly that the very concept of watching the sky will have taken on new meanings we cannot imagine. The 12,000-year cycle we're contemplating tonight is not arbitrary. It's a time span that appears again and again in different contexts, both cosmic and terrestrial. It's roughly half of what astronomers call a precession cycle, the slow wobble of Earth's axis that takes about 26,000 years to complete. It's close to the span of time since the end of the Younger Dryas, the last gasp of the Ice Age that shaped the world we know today. It's a period that encompasses all of human civilization, from the first agricultural settlements to the modern day. If 3-Eye Atlas really does return every 12,000 years, then its last visit would have been around 10,000 BCE. Picture the Earth at that time. The great ice sheets that had covered much of North America and Europe were retreating. Sea levels were rising as billions of tons of ice melted and flowed back to the oceans. The climate was warming, sometimes gradually, sometimes in dramatic jumps. Forests were advancing into areas that had been tundra. Animals and plants were migrating, adapting, evolving in response to these massive changes. And humans? We were there, of course, small bands of hunter-gatherers, following the herds, learning the new landscapes that the retreating ice revealed. In some places, we were just beginning to experiment with the cultivation of plants, the domestication of animals. We were telling stories around fires, painting on cave walls, developing the languages and myths that would become the foundations of all future cultures. If a comet appeared in the sky during that time, bright enough to be seen with the naked eye, it would have been witnessed by our ancestors. They would have watched it night after night, perhaps for weeks or months, as it traced its path across the sky. They would have wondered about it, told stories about it, perhaps feared it or revered it. But they would have had no way to record its passage in a way that we could decipher today. No written language existed, no mathematical system capable of calculating orbits, just memory, passed down through generations in stories and songs, gradually changing with each telling until the original observation was lost in the mists of myth. This is one of the profound gaps in our knowledge. We have written records going back perhaps 5,000 years. We have archaeological evidence going back further, tens of thousands of years. But the sky leaves no fossils. Comets come and go without leaving physical traces we can excavate. unless they impact Earth directly, and thankfully, that's extremely rare, they exist only in the moment of their passing. All those comets that grace the skies of the ancient world, witnessed by countless generations of humans who looked up in wonder just as we do, are lost to us. We can calculate backwards using the orbits of known comets, and sometimes we can match these calculations to historical records. Halley's Comet, for instance, appears in Chinese chronicles, in medieval tapestries, in the writings of astronomers throughout history. But Halley's has a relatively short period of 76 years. A comet with a 12,000-year period would have appeared only once since the invention of writing, unless, of course, it fragmented on an earlier pass, and what we saw as 3I Atlas was just one piece of a larger body that broke apart long ago. In that case, there might be other fragments, following similar but not identical orbits. Some might have periods of 11,000 years, others 13,000 years. They would be siblings, born from the same parent body, each carrying part of the original mass on its own journey through time. This kind of fragmentation is not unusual for comets. Many of the meteor showers we observe each year are the result of cometary debris spread along orbital paths. The Perseids, which peak every August, are the remnants of Comet Swift-Tuttle. The Leonids come from Comet Tempel-Tuttle. When Earth passes through these debris streams, the tiny particles, most no bigger than grains of sand, burn up in our atmosphere, creating the streaks of light we call shooting stars. It's possible that 3I Atlas has created its own debris stream, one that Earth might encounter at some point in its orbit. If so, it would be a very sparse stream, given the comet's long period and recent fragmentation. But somewhere in our future, perhaps in a few years or decades, we might pass through the cloud of dust that was once 3I Atlas. On that night, new shooting stars would appear, each one a tiny piece of our mysterious visitor, completing its journey from the edge of the solar system to Earth's atmosphere. The mathematics of orbital mechanics, the physics that governs these cosmic trajectories, is both beautifully simple and endlessly complex. At its heart is Newton's law of universal gravitation. Every mass attracts every other mass with a force proportional to their masses, and inversely proportional to the square of the distance between them. This simple relationship, discovered over 300 years ago, allows us to predict the motions of planets, moons, asteroids, and comets with extraordinary precision. But when multiple bodies are involved, when we account for the gravitational influences of all the planets, the situation becomes what mathematicians call a many-body problem, which has no general analytical solution. We can simulate it with computers, calculating the forces moment by moment, step by step, but there's always uncertainty that grows with time. For a comet with a 12,000-year period, this uncertainty is significant. The gravitational influences of the giant planets, Jupiter, Saturn, Uranus, and Neptune, can alter its orbit slightly with each pass. A close encounter with Jupiter, for instance, could shorten or lengthen the period by years or even decades. Over many orbits, these small changes accumulate. A comet that starts with a 12,000-year period might, after several orbits, have a period of 11,500 years or 12,500 years. Its path through the inner solar system might shift, bringing it closer to or farther from the Sun at perihelion. These are the kinds of subtle variations that make each apparition unique, even if the comet itself remains the same. And then there are the non-gravitational forces. As a comet approaches the Sun and begins to heat up, the vaporizing ice creates jets of gas that act like tiny rockets, pushing the comet in unpredictable ways. This is called outgassing, and it can significantly alter a comet's trajectory. The effect depends on the comet's rotation, its shape, the distribution of ice on its surface, factors that are difficult to measure and impossible to predict far in advance. For 3I Atlas, the outgassing that contributed to its fragmentation might also have changed its orbit, or the orbits of its fragments, in ways we'll never fully know. Yet despite all these uncertainties, There's something comforting about the fundamental predictability of celestial mechanics. The same laws that govern the fall of an apple govern the orbit of a comet. The same mathematics that describes the motion of planets describes the trajectory of Three-Eye Atlas. We're all part of the same physical system, subject to the same forces, following the same rules. In this sense, the comet is not alien or other. It is part of our extended family, a distant relative following its own path but bound to us by the invisible threads of gravity. As we continue our contemplation, let's drift deeper into the realm of cosmic time. The 12,000-year period we're imagining is long by human standards, but relatively brief by cosmic ones. Our solar system is about 4.6 billion years old. If Three-Eye Atlas has been orbiting for even a fraction of that time, it has completed hundreds of thousands of orbits, each one slightly different from the last, but all following the same general pattern. The long, slow fall inward, the brief, bright passage near the sun, and then the long, slow climb back to the darkness. Imagine compressing all those orbits into a single year. If each 12,000-year orbit took just one day, then the comet would have been circling for over 1,000 years. In this compressed timescale, all of human history from the first civilizations to the present day would occupy less than half a day. The rise and fall of empires, the development of science and technology, the entire story of our species' cultural evolution would be compressed into a few hours of the comet's endless circling. This kind of perspective shift can be deeply calming. Our individual lives, with all their stresses and concerns, are even briefer flashes in this cosmic timeline. The problems that keep us awake at night, the anxieties that tighten our shoulders and quicken our heartbeats, are real and valid in our immediate experience. But when we place them in this larger context, when we see them from the perspective of a comet on a 12,000-year journey, they take on a different quality. They become part of the texture of existence, temporary perturbations in the flow of time, no more permanent than the warming of a comet as it passes near the sun. This is not to diminish the importance of our lives or our concerns. Rather, it's to place them in a context that can bring peace. We are part of something vast and ongoing. Our troubles will pass just as everything passes. The comet continues its journey. The planets continue their orbits. The galaxy continues its rotation. And we, for this brief moment, are witnesses to it all. We have the extraordinary privilege of awareness, of being able to contemplate these vast scales and find our place within them. This silence of space is something we can only imagine. Here on Earth, even in the quietest moments, there is sound, the rustle of leaves, the distant hum of civilization, the whisper of our own breathing. But in space, in the vacuum through which Three-Eye Atlas travels, there is absolute silence. No medium for sound waves to propagate through. No vibrations except those carried within solid objects themselves. The comet's journey is utterly, profoundly quiet. Yet this silence is full of activity. Solar radiation streams outward from the sun at the speed of light. Magnetic fields twist and spiral. Charged particles flow in great currents. Gravitational waves, ripples in space-time itself, pass through everything, carrying information about distant cosmic events. The comet moves through all of this, a small island of matter in an ocean of energy and force fields. It is affected by all of it, its orbit shaped by gravity, its surface sculpted by radiation, its tail blown by the solar wind. But it makes no sound, it raises no voice, it simply continues, patient and persistent, on its ancient path. When we observed Three-Eye Atlas from Earth, we were seeing light that had travelled for minutes to reach us. The photons that entered our telescopes had bounced off the comet's surface or been emitted by its glowing gases, then travelled across millions of miles of empty space to reach our instruments. In a sense, we were looking into the past, seeing the comet as it was minutes before, not as it was in the moment of observation. This delay, caused by the finite speed of light, means that all astronomy is a form of time travel. The farther we look into space, the further we look back in time. For 3i Atlas, this delay was minimal, a matter of minutes. But the principle connects us to the deepest observations we can make. When we look at distant galaxies, we see them as they were billions of years ago. When we observe the cosmic microwave background, we're seeing the universe as it was just 380,000 years after the Big Bang. We are surrounded by the past, bathed in ancient light from every direction. The present moment, the absolute now, exists only right where we are. Everything else we see is history, arriving at the speed of light. This interweaving of space and time, this fundamental connection between distance and duration, is one of the profound insights of modern physics. It tells us that the universe is not a static stage on which events occur, but a dynamic, evolving system where space and time are intimately connected. The comet's journey is not just through space, but through space-time, following a path that curves through both spatial and temporal dimensions. As 3i Atlas fragmented, each piece began its own journey through space-time. They started together, parts of a whole, but the fragmentation event gave each fragment a slightly different velocity, a slightly different direction. Over time, these small differences will accumulate. The fragments will spread out along the orbital path, some moving slightly faster, others slightly slower. Eventually, they will be distributed around the entire orbit, a river of ice and dust following the same general path, but no longer travelling as a single body. This dispersion is another form of cosmic clock. The rate at which the fragments spread out depends on the specifics of the fragmentation event and the subsequent forces acting on each piece. By observing this dispersion over time, if we could track the fragments for years or decades, we could work backwards to understand better what happened during the fragmentation. But the fragments are too small, too faint, and moving away too quickly for our current instruments to track. They have disappeared into the darkness, carrying their secrets with them. Yet the story doesn't end with disappearance. In the cosmic scheme, nothing truly disappears. It only transforms, relocates, waits. The fragments of 3i Atlas are still out there, continuing their journey. In 12,000 years, or perhaps 11,000 or 13,000, depending on how the fragmentation affected their orbits, they will return to the inner solar system. By then, they may have spread out so much that they arrive over a period of years or decades rather than all at once. Each fragment will have its own moment of warming, its own brief brightening, its own contribution to the ongoing story. Will humanity be here to witness their return? It's a question that naturally arises when we contemplate such vast timescales. 12,000 years ago, we were just beginning to develop agriculture. 12,000 years from now, we might be unrecognizable to our current selves. We might have spread throughout the solar system, perhaps even to nearby stars. We might have developed technologies that seem like magic to us now, or we might have faced challenges we couldn't overcome, leaving only ruins for some other intelligence to puzzle over. But these are concerns for another time, another contemplation. Tonight, we're simply holding space for wonder. We're allowing ourselves to feel the vast, patient rhythms of the cosmos. We're recognizing that we are part of something so much larger than our daily experience suggests. The comet's journey continues whether we observe it or not. The universe unfolds according to its own logic, its own time scales, its own purposes, if purposes they are. In the gentle darkness where you rest now, breathing slowly and deeply, you can feel yourself connected to these cosmic cycles. Your body is made of atoms forged in stars, arranged temporarily in this particular pattern we call you. The carbon in your cells, the oxygen in your blood, the calcium in your bones, all of it has been on its own cosmic journey, no less remarkable than that of any comet. You're not separate from the universe. You're a part of it, a temporary arrangement of its substance, granted the extraordinary gift of awareness. The contemplation of vast scales and deep time can sometimes make us feel small, insignificant. But there's another way to see it. We are the universe becoming aware of itself. Through our eyes, the cosmos observes its own beauty. Through our minds, it contemplates its own mysteries. Through our wonder, it experiences awe at its own majesty. We are not insignificant. We are the significance. We are the part that wonders, that questions, that seeks to understand. As we move into the second phase of our journey tonight, we'll explore the grand clockwork that governs these cosmic cycles. We'll delve deeper into the mechanics of orbits, the dance of gravity and momentum that keeps everything in motion. We'll see how 3i Atlas fits into this larger pattern, this celestial choreography that has been playing out for billions of years. The stage is set, the players are in motion, and we have front row seats to one of the universe's most patient performances. The transition from one thought to another, from one scale to another, is like the comet's own journey from light to darkness and back again. There are no sharp boundaries, no sudden changes. Everything flows into everything else, connected by the invisible threads of physical law and cosmic history. As you continue to breathe, to relax, to let your mind drift with these thoughts, you're participating in this flow. You're not just observing the cosmic dance, you're part of it. Consider how we mark time here on Earth. Our clocks tick in seconds, minutes, hours. Our calendars track days, months, years. These units are based on astronomical cycles, the rotation of Earth, the orbit of Earth around the Sun, the phases of the Moon. We've borrowed the rhythms of celestial bodies to organize our lives. In a sense, we live by cosmic time, even when we're not aware of it. Every sunrise, every season, every year that passes is a reminder that we're passengers on a planet that's following its own orbit through space. But these familiar cycles are just the smallest, quickest rhythms in a vast symphony of cosmic periods. The Moon's orbit around Earth is gradually spiraling outward. In 1 billion years, it will be significantly farther away, and Earth's day will be longer. The Sun itself orbits the center of our galaxy, completing one circuit every 230 million years, a period sometimes called a galactic year. The galaxy itself is moving, part of a local group of galaxies that are gravitationally bound together, and this local group is moving through space, part of larger structures that span hundreds of millions of light years. At every scale, there is motion, there are cycles, there are periods of repetition and return. 3i Atlas, with its hypothetical 12,000-year orbit, is participating in this cosmic dance at its own scale, with its own rhythm, is like a note in a vast piece of music contributing its own frequency to the overall harmony. The fact that we happen to observe it during our brief moment of awareness is a form of cosmic synchronicity. Out of all the possible times in its orbit, out of all the possible moments in human history, it appeared just when we had developed the technology to see it and the knowledge to understand what we were seeing. This synchronicity extends beyond just the timing. The comet appeared during a period when humanity is grappling with its own place in the cosmos. We've discovered thousands of planets orbiting other stars. We've detected gravitational waves from colliding black holes. We've photographed the event horizons of supermassive black holes. We're in the midst of a revolution in our understanding of the universe, and every new discovery, every visiting comet, every unexpected observation adds another piece to the puzzle. The fragmentation of 3i Atlas might seem like a loss. We'll never see this particular comet again in its original form. But it's also a transformation, a redistribution of matter and energy that will have consequences we can't fully predict. Some of the dust will eventually fall into the sun, adding its ancient substance to our star's mass. Some will drift outward, perhaps leaving the solar system entirely, carrying information about our cosmic neighborhood to interstellar space. And some will continue to orbit, perhaps seeding future comets, future meteor showers, future moments of wonder for observers we can't imagine. This is the way of the cosmos. Nothing is permanent, but nothing is truly lost. Everything transforms, everything continues in new forms, everything participates in the ongoing evolution of the universe. The ice that was 3i Atlas has been ice before and will be ice again. The atoms that composed it have been part of other structures and will be part of others in the future. The energy that held it together has been transferred to its fragments, to the light it emitted, to the gravitational waves its motion generated. The story continues, even when individual chapters end. As we prepare to delve deeper into the clockwork of the cosmos, into the precise mechanisms that govern these vast cycles, let's carry with us this sense of continuity, of connection, of participation in something magnificent. The universe is not just something we observe, it's something we're part of. Every breath we take exchanges atoms with the atmosphere. Every moment we exist, we're exchanging energy with our environment. We're not separate from the cosmic dance. We're dancers ourselves, moving to rhythms both quick and slow, both local and universal. The comet's journey is our journey, in a sense. We too are travelers through space and time, following our own orbits, experiencing our own cycles of approach and retreat, warming and cooling, gathering and dispersing. The difference is one of scale, not of kind. We're all part of the same vast, patient, beautiful process. And now, as we transition into contemplating the deeper mechanics of this cosmic clockwork, we find ourselves at a threshold. Behind us is the story of a single comet, a brief visitor that captured our attention and then faded away. Ahead of us is the larger system of which it was a part, the grand mechanism that keeps everything in motion. We're about to explore how gravity and momentum conspire to create the elegant, predictable, yet endlessly surprising patterns we see in the heavens. We're about to see how 3i Atlas was not an exception but an example, not an anomaly but an affirmation of the deep order that underlies apparent chaos. The universe has been keeping time long before humans invented clocks. It has been tracking cycles, marking periods, maintaining rhythms since the first particles condensed from the primordial fire of the Big Bang. Every orbit is a tick of a cosmic clock. Every return is a chime marking the passage of eons. And we, in our brief moment, have the privilege of listening to this cosmic timepiece, of noting its rhythms, of adding our own small voices to its vast ongoing song. In the space between heartbeats, in the pause between breaths, we can almost hear it, the silent music of the spheres, the gravitational symphony that keeps everything in motion. 3 Atlas was just one instrument in this orchestra, playing its part for a brief moment before falling silent. But the music continues, the dance goes on, and we are here now, witnesses to wonder, participants in mystery, brief notes in an eternal song. As we move forward into the mechanics of this cosmic clockwork, remember that we're not leaving the comet behind. We're expanding our view to see the system of which it was a part. We're zooming out to appreciate the full majesty of the mechanism that brought it to us and will, perhaps, bring it back again. The journey continues, the mystery deepens, and the wonder only grows. Now, let us turn our attention to the grand cosmic clockwork itself, the silent machinery that orchestrates these immense journeys through space and time. Imagine, if you will, the solar system not as a collection of isolated objects, but as an intricate timepiece of impossible scale and complexity. Every planet, every moon, every asteroid and comet is a gear in this mechanism, each one meshing with the others through the invisible teeth of gravity, turning in precise ratios, marking out periods that range from hours to millions of years. The image of clockwork might seem too mechanical, too rigid for something as fluid and dynamic as space. But there's a deep truth in this metaphor. The cosmos operates with a precision that would make the finest Swiss watchmaker weep with envy. The planet Neptune, for instance, orbits the Sun once every 164.8 Earth years, and it does so with such reliability that we can predict its position centuries in advance. The Moon circles Earth every 27.3 days, so regularly that ancient civilizations built their calendars around its phases. These are not approximations or averages. These are precise periods, maintained by the fundamental laws of physics with an accuracy that surpasses any timepiece humans have ever built. Yet unlike a mechanical clock, which gradually runs down without winding, the cosmic clockwork is essentially perpetual. The energy for its motion came from the collapse of the original nebula that formed our solar system. As that vast cloud of gas and dust contracted under its own gravity, it began to spin, and that angular momentum has been preserved ever since. It has been transferred from particle to particle, from gas to dust to planet, but never lost. The Earth spins because the cloud from which it formed was spinning. The Moon orbits because the debris disk from which it coalesced was orbiting. And 3i Atlas follows its long ellipse because somewhere, sometime in the deep past, it acquired just the right combination of speed and direction to establish that particular path. This is one of the most profound principles in physics, the conservation of angular momentum. In the absence of external forces, a spinning or orbiting body will continue spinning or orbiting forever. And while there are subtle forces at work, tidal friction, solar wind, gravitational perturbations from passing stars, they are so small that the basic patterns persist for billions of years. The clockwork keeps ticking, powered by the momentum of its own history. Think about what this means for a hypothetical 12,000-year comet. If 3i Atlas, or its parent body, has been following this orbit since the early days of the solar system, it has completed nearly 400,000 circuits, each one slightly different due to planetary perturbations, but all following the same basic pattern. 400,000 approaches to the Sun, 400,000 retreats to the outer darkness. If we could somehow watch all these orbits overlaid, we would see not a single line but a fuzzy cable, a bundle of paths that wind around each other, sometimes diverging, sometimes converging, but always maintaining the same general shape. This orbital stability is remarkable when you consider the forces involved. As the comet falls inward from the Oort cloud, it accelerates from a mere crawl, perhaps a few hundred meters per second, to speeds of over 40 kilometers per second as it whips around the Sun. The gravitational force it experiences changes by factors of millions. The temperature of its surface swings from near absolute zero to hundreds of degrees. Yet through all these extremes, the basic mathematics of its orbit remains unchanged. Energy is conserved. Angular momentum is conserved. The path, while modified by various perturbations, maintains its essential character. The precision of these cosmic movements becomes even more impressive when we consider that everything is moving relative to everything else. The Sun itself is not stationary. It's orbiting the galactic center at about 230 kilometers per second, carrying the entire solar system with it. From a galactic perspective, the comet's path is not a simple ellipse, but a complex helix, spiraling through space as the whole system moves through the galaxy. Yet within the reference frame of the solar system, the orbit remains stable and predictable. This brings us to one of the beautiful insights of relativity. There is no absolute reference frame, no fixed stage on which cosmic events play out. Every motion is relative to something else. The comet orbits the Sun, but from the comet's perspective, it's the Sun and planets that are moving in complex patterns around it. Both perspectives are equally valid. The universe has no preferred viewpoint, no special position from which everything else should be measured. We each carry our own reference frame with us, our own valid perspective on the cosmic dance. In our everyday experience, we're used to things running down, wearing out, coming to a stop. A pendulum swings more and more slowly until it hangs motionless. A spinning top wobbles and falls. A thrown ball eventually comes to rest. This is because of friction, air resistance, and other forces that dissipate energy. But in the vacuum of space, these forces are absent or negligible. There's no air to create drag, no surface to generate friction. Objects in motion remain in motion, not for seconds or hours, but for billions of years. This is why we can still see the effects of events that happened when the solar system was young. The asteroid belt between Mars and Jupiter contains fragments from collisions that occurred billions of years ago, still following the orbits established by those ancient impacts. The Oort cloud itself is thought to be composed of objects that were gravitationally expelled from the inner solar system during the period of planetary formation, flung outward by close encounters with Jupiter and Saturn, and now orbiting in the deep freeze, waiting for something to send them falling back inward. Perhaps 3I Atlas was one of these exiled objects, a piece of the original protoplanetary disk that was cast out during the chaotic early days when the planets were still finding their orbits. If so, its 12,000-year cycle might be telling us something about the conditions in the early solar system, about the specific gravitational interaction that established its orbit. Every comet is a messenger from the past, but long-period comets like 3I Atlas are the most ancient messengers of all, carrying information from the very dawn of our cosmic neighborhood. The mathematics that describes these orbits was first worked out by Johannes Kepler in the early 1600s, based on careful observations of planetary positions. Kepler discovered 3 laws that govern orbital motion. First, orbits are ellipses with the Sun at one focus. Second, a line connecting a planet to the Sun sweeps out equal areas in equal times. Third, the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. These laws, derived from observation, were later explained by Newton's theory of gravity, and are now understood as consequences of the inverse square law of gravitational attraction. For a comet with a 12,000-year period, Kepler's third law tells us that its average distance from the Sun, the semi-major axis of its orbit, is about 470 astronomical units. 1 astronomical unit, or AU, is the average distance from Earth to the Sun, about 150 million kilometers, so the comet's orbit extends to 470 times this distance, about 70 billion kilometers from the Sun. At this distance, the Sun would appear as just the brightest star in the sky, perhaps as bright as the full moon appears from Earth, but still just a point of light, not the disk we see from our closer vantage point. But this average distance is misleading because the orbit is highly elliptical. At its closest approach, perihelion, the comet might come within 1 or 2 AU of the Sun, inside Earth's orbit. At its farthest, aphelion, it might reach out to nearly 940 AU, almost 1,000 times Earth's distance from the Sun. This extreme ellipse means the comet spends most of its time in the outer reaches, moving slowly through the cold and dark, and only a brief period, perhaps a year or 2 out of every 12,000, in the inner solar system where we can observe it. The shape of this orbit, this long, narrow ellipse, is determined by the comet's energy and angular momentum. If it had slightly more energy, the orbit would be larger, the period longer. If it had slightly less, the orbit would be smaller, the period shorter. If it had exactly the right amount of energy, the orbit would not be closed at all. It would be a parabola or hyperbola, and the comet would make only a single pass through the solar system before escaping to interstellar space. The fact that 3I Atlas was on a closed orbit means its energy was precisely tuned to keep it bound to our Sun, despite the enormous distance of its travels. This precise tuning is not the result of design or purpose, but of selection. Over the history of the solar system, countless objects have passed through with various energies and trajectories. Those with too much energy escaped to interstellar space. Those with too little energy either collided with planets or fell into the Sun. Only those with just the right parameters established stable long-term orbits. 3I Atlas, or its parent body, was one of the survivors, one of the objects that found a stable niche in the cosmic clockwork. But even stable orbits are not perfectly stable. Over very long timescales, various effects can alter them. The gravitational influence of passing stars can perturb objects in the Oort cloud, changing their orbits or sending them falling inward. The galaxy itself has a tidal effect, stretching and compressing orbits as the solar system moves through regions of varying gravitational field. Even the slow evaporation of the Sun as it converts mass to energy through nuclear fusion has a cumulative effect over billions of years. These perturbations are part of what makes the cosmic clockwork so fascinating. It's not a simple, repetitive mechanism, but a complex, chaotic system with multiple interacting parts. The motion of every object affects every other object, creating a web of gravitational influences that can produce surprising results. Sometimes these interactions lead to orbital resonances, where objects settle into orbits with periods that are simple ratios of each other. Jupiter's moons Io, Europa, and Ganymede, for instance, are locked in a 4-2-1 resonance, completing 4, 2, and 1 orbits respectively in the same time period. Could 3i Atlas be in some kind of resonance with another solar system body? It's possible, though difficult to determine without more observations. A 12,000-year period doesn't match any obvious resonance with the known planets, but there could be subtle relationships we haven't recognized. Or perhaps the resonance is not with a planet but with the galactic tide, or with the periodic passage of the solar system through the denser regions of the galaxy's spiral arms. These are the kinds of questions that keep astronomers awake at night in the best possible way. Every observation opens new questions, new possibilities, new connections to explore. The cosmic clockwork is not a solved problem but an ongoing mystery, revealing new layers of complexity the more closely we examine it. And each comet that visits us, each fragment of ancient ice that falls sunward, adds another piece to our understanding of this grand mechanism. The idea of celestial mechanics as clockwork has deep roots in human thought. Ancient civilizations recognized the regular patterns of celestial motion and used them to create calendars, to navigate, to time agricultural activities. The Antikythera mechanism, recovered from a shipwreck off the Greek coast, is a 2,000-year-old mechanical computer that calculated the positions of planets and predicted eclipses. It shows that humans have long understood the cosmos as a kind of machine, operating according to discoverable rules. But it wasn't until Newton that we had a theoretical framework to explain why the cosmic clockwork operates as it does. His law of universal gravitation showed that the same force that causes an apple to fall from a tree also keeps the moon in orbit around Earth, and Earth in orbit around the Sun. This unification of terrestrial and celestial physics was revolutionary. It meant that the heavens were not a separate divine realm, operating according to different laws, but part of the same physical universe we inhabit. This democratization of the cosmos, this recognition that the same laws apply everywhere, is what allows us to understand objects like 3i Atlas. We can apply the same physics we test in laboratories on Earth to predict the motion of a comet billions of kilometers away. We can use the same mathematics that describes a pendulum to calculate orbital periods. The cosmic clockwork operates according to universal principles that we can discover and understand. Yet understanding the principles doesn't diminish the wonder. If anything, it enhances it. To know that the gentle arc of 3i Atlas across our sky was determined by the conservation laws of physics, that its appearance was as inevitable as the sunrise given its initial conditions, that its fragmentation was the result of well-understood thermal and tidal stresses, this knowledge doesn't make the event less remarkable. It makes it more so. It connects this singular event to the deep structure of reality, to the fundamental laws that govern everything from subatomic particles to galaxy clusters. As you lie here, breathing steadily, feeling the slow rhythm of your heartbeat, you're experiencing your own participation in the cosmic clockwork. Your heart beats because of electrochemical processes governed by the same fundamental forces that shape comet orbits. The calcium ions that trigger your muscle contractions were forged in the cores of dying stars, expelled in supernovae, incorporated into the nebula that formed our solar system, and eventually assembled into your body. You're not observing the cosmic clockwork from outside, you're one of its components, one of its temporary but essential mechanisms. The rhythm of your breathing, perhaps 8 to 12 breaths per minute, is fast compared to the rhythms of the cosmos. In the time it takes you to complete one breath, light travels millions of kilometers. Earth rotates about 0.3 degrees on its axis. The moon moves about 30 meters in its orbit, and somewhere in the outer darkness the fragments of 3Y Atlas continue their journey, moving perhaps a few kilometers farther from the sun, their speed gradually decreasing as they climb out of the sun's gravitational well. But from another perspective, your breathing is incredibly slow. In the time it takes you to complete one breath, countless atoms in your body vibrate trillions of times. Electrons orbit atomic nuclei quadrillions of times. Photons of light cross your retina billions of times. You contain your own clockwork at microscopic scales, mechanisms operating at frequencies far beyond perception, yet essential to your existence. This hierarchy of rhythms from the quantum to the cosmic is one of the most beautiful aspects of our universe. Every scale has its own characteristic timescales, its own natural frequencies, its own rhythms and cycles, and somehow they all mesh together, each scale emergent from the ones below it, each one contributing to the ones above it. Your consciousness emerges from neural activity operating at millisecond timescales. Your life unfolds over decades. Your species evolves over millions of years, and the comet that briefly visited our skies connects us to cycles spanning hundreds of millions of years. As we prepare to explore the specific observations and data that revealed 3M Atlas to us, let's carry with us this sense of the cosmic clockwork, this appreciation for the precise yet complex mechanisms that govern celestial motion. The comet didn't appear randomly. It arrived precisely when the clockwork of its orbit brought it to us. And our ability to observe it, to track it, to begin to understand it, was only possible because we have learned to read the time signatures of the cosmic clock, to recognize the rhythms and patterns that play out on scales far beyond our direct experience. The universe is patient with its secrets, revealing them slowly to those who watch carefully, who track the patterns, who learn to see the clockwork behind the apparent randomness. Every astronomer who pointed a telescope at 3 Atlas was reading the cosmic clock, noting the position of one small hand on a vast dial, and together, observation by observation, night by night, they assembled a picture of this visitor's brief passage through our neighborhood, adding one more data point to our ever-growing understanding of the magnificent mechanism we inhabit. The transition from the grand clockwork to the specific details of observation is like adjusting the focus of a telescope, bringing a fuzzy point of light into sharp relief. We've been contemplating the vast mechanism. Now we turn to the delicate work of observation, the careful gathering of photons that traveled millions of kilometers to tell us about a chunk of ice we'll never touch, a visitor we'll never see again in the same form. This is the beautiful paradox of astronomy. We study the unreachable, we measure the untouchable, we come to know objects we can never visit, and we do it all by collecting and analyzing light, the silent messenger that connects us to the cosmos. The story of how we detected and studied through Atlas is a testament to human ingenuity and patience. It's a story of technology and technique, of computers and calculations, but ultimately it's a story of curiosity, of humans who choose to spend their nights watching the sky, searching for faint whispers of light that might tell us something new about our cosmic neighborhood. These modern astronomers are the inheritors of an ancient tradition, stretching back to the first humans who looked up and wondered what those moving lights might be. But where our ancestors had only their eyes, we now have instruments of extraordinary sensitivity, mechanical eyes that can see colors invisible to us, that can detect single photons, that can track objects far too faint for human vision. The Atlas system that first detected our mysterious visitor consists of 4 telescopes, 2 in Hawaii, 1 in South Africa, and 1 in Chile. Each telescope has a primary mirror just 0.5 meters in diameter, modest by modern standards, where some telescopes have mirrors over 10 meters across. But what Atlas lacks in size, it makes up for in dedication and coverage. These telescopes don't peer deeply at small patches of sky. Instead, they survey vast swathes of the heavens, taking multiple images of the same regions night after night, searching for anything that moves or changes. The basic principle is beautifully simple. Stars, being so far away, appear fixed in the sky. They maintain the same positions relative to each other night after night, year after year. But objects in our solar system, asteroids, comets, planets, are much closer, and they move noticeably against the stellar background. By comparing images taken minutes or hours apart, astronomers can spot these moving objects, track their motion, and calculate their orbits. It's like standing in a forest and identifying which trees are actually camouflaged animals by watching for movement. On the night when 3 Atlas was first detected, it appeared as nothing more than a faint dot of light, barely distinguishable from the background noise of the image. The CCD cameras that captured its light are marvels of technology, able to convert individual photons into electrical signals with high efficiency. Each pixel in these cameras acts like a tiny bucket, collecting photons during the exposure. When enough photons accumulate, they create a signal strong enough to be measured and recorded. The faint light from 3I Atlas, traveling for millions of kilometers through space, ended its journey by knocking electrons loose in a silicon chip, creating a pattern of electrical charges that, when read out and processed, revealed the comet's presence. But a single detection is never enough in astronomy. It could be a cosmic ray hit, a satellite, a flaw in the detector, or any number of other false signals. Real objects must be confirmed through multiple observations. And so, night after night, the telescopes return to the same region of sky, capturing more images, tracking the object's motion, building up a record of its path across the heavens. Each observation added another point to the growing trajectory, another constraint on the possible orbit. The software that processes these images is as crucial as the hardware that captures them. Modern astronomical surveys generate enormous amounts of data, terabytes per night. No human could examine all these images by eye, looking for moving objects. Instead, sophisticated algorithms compare images, identify potential moving objects, calculate preliminary orbits, and flag interesting candidates for human review. It's a partnership between human intuition and machine processing, each complementing the other's strengths. When 3 Atlas was first flagged by the software, it would have appeared on an astronomer's screen as a series of dots marking its position at different times, overlaid on an image of the star field. The astronomer would have examined these positions, checking that they formed a consistent trajectory, that the brightness was reasonable for a real object, that there were no obvious problems with the detection. Only after passing these checks would the object be reported to the Minor Planet Center, the international clearinghouse for observations of small solar system bodies. The initial observation suggested something unusual about this object. Its motion was fast, faster than typical for a comet at that distance from the Sun. This high speed was one of the factors that initially led to speculation about an interstellar origin. Objects from outside our solar system enter with excess velocity, the speed they had while orbiting other stars plus the speed gained by falling into our Sun's gravitational well. This extra speed means they follow hyperbolic orbits, passing through once and never returning. But as more observations accumulated, the picture became more complex. The object's position wasn't following the predicted path exactly. There were small deviations, systematic differences between where it should be based on a pure gravitational orbit and where it actually appeared. These deviations could be explained by non-gravitational forces, the rocket effect of gas jets as the comet's ice sublimated in the Sun's heat. This outgassing is common in comets, and can significantly affect their orbits, making precise prediction challenging. The spectrum of light from 3I Atlas provided additional clues about its nature. By spreading the light out into its component colors, astronomers could identify the signatures of different molecules in the comet's coma. Water, carbon dioxide, and various organic compounds each absorb and emit light at specific wavelengths, creating a kind of chemical fingerprint. The spectrum of 3I Atlas showed it was rich in water ice, typical of long-period comets from the outer solar system. But then came the unexpected development, the fragmentation. Over a period of days, observers watched as the single point of light began to elongate, then split into multiple components. This wasn't a violent explosion, but a gradual coming apart, like a clump of wet sand slowly dissolving in water. The brightness of the comet decreased as it fragmented. The total light spread among multiple pieces, each too faint to track individually with most telescopes. Fragmentation events are not uncommon in comets, but they're still not fully understood. The leading theories involve either thermal stress from uneven heating as the comet rotates, tidal stress from the sun's gravity acting differently on the near and far sides of the comet, or the release of pressure from volatile gases building up beneath the surface. For 3I Atlas, approaching the sun for perhaps the first time in 12,000 years, the thermal shock of solar heating after millennia in the deep freeze might have been too much for its fragile structure to withstand. The Hubble Space Telescope was enlisted to observe the fragmentation in detail. With its superior resolution and sensitivity, Hubble could distinguish individual fragments that appeared as a single blurred source to ground-based telescopes. The images showed at least 4 major pieces, each surrounded by its own cloud of dust and gas, drifting slowly apart as they continued along nearly identical orbits. It was like watching a slow-motion replay of a cosmic dissolution, played out over days and weeks rather than seconds. These Hubble observations were precious. Telescope time on Hubble is extremely limited and highly competed for. Thousands of astronomers submit proposals each year, and only a fraction are approved. The decision to observe 3 Atlas with Hubble reflected the scientific community's recognition that this was a unique event, a chance to study cometary fragmentation in unprecedented detail. Every photon collected by Hubble's mirror was valuable data, contributing to our understanding of how comets die or transform. The data from all these observations, positions, brightness measurements, spectra, images, were shared freely among astronomers worldwide. This is one of the beautiful aspects of modern astronomy, the spirit of open collaboration. Data that cost millions of dollars and countless hours to collect are made available to anyone who wants to analyze them. A student in India can download the same Hubble images that professional astronomers at major universities are studying. An amateur astronomer in Brazil can contribute observations that help refine the orbit. The study of 3I Atlas became a global effort, with contributions from observers on every continent. As the fragments of 3I Atlas faded from view, too faint for even our best telescopes to track, the focus shifted from observation to analysis. What could we learn from the data we had collected? What did the fragmentation tell us about the comet's structure? Could we work backwards from the observed motion to determine where this object came from and where it was going? The orbital calculations were particularly intriguing. By combining all the observations and accounting for the non-gravitational forces as best as possible, astronomers could trace the comet's path backward and forward in time. The backward extrapolation suggested the comet had last been in the inner solar system many thousands of years ago, possibly around 12,000 years, though the uncertainty was large. The forward extrapolation was even more uncertain, because the fragmentation had altered the orbits of the pieces in unknown ways. This uncertainty is fundamental to our story. We can never know with absolute precision where 3I Atlas came from, or where its fragments are going. The universe keeps some secrets, revealing only what can be gleaned from brief observations during fleeting encounters. But this uncertainty is not a failure. It's an invitation to wonder, to imagine, to construct possible scenarios that fit the available data. The ghost in the data, the pattern of observations that defined 3I Atlas, tells us as much about the process of discovery as it does about the comet itself. It shows us how modern astronomy works: patient observation, careful analysis, global collaboration, and always the willingness to be surprised. The universe rarely behaves exactly as we expect, and it's in these deviations from expectation that we learn the most. Consider what it means that we can detect and track an object like 3I Atlas at all. This chunk of ice, perhaps a few kilometers across, was visible to us from a distance of hundreds of millions of kilometers. The photons that revealed its presence had traveled for minutes through the vacuum of space, maintaining their direction and energy with perfect fidelity, carrying information about the comet's composition, temperature, and motion. The fact that we can extract all this information from such faint whispers of light is a testament to both the reliability of physical laws and the ingenuity of human technology. The instruments we use to make these observations are themselves products of cosmic evolution. The silicon in the CCD detectors was forged in stellar cores. The glass in the telescope mirrors contains oxygen that was created in massive stars. The computers that process the data run on electricity generated by various means, but ultimately all energy on Earth traces back to nuclear fusion, either in our sun or in the stars that came before. We use the products of cosmic processes to study cosmic phenomena. We are the universe investigating itself. As we collected data on 3I Atlas, we were also collecting data on ourselves, on our capabilities and limitations. We learned what our current technology can and cannot do. We identified gaps in our coverage, times when no telescope was watching, regions of sky we don't monitor closely enough. Each observation was not just a measurement of the comet, but a test of our systems, a calibration of our abilities. The fragmentation of 3I Atlas was particularly valuable in this regard. Fragmentation events are natural experiments that we cannot replicate in laboratories. We can't take a comet, subject it to the conditions of the inner solar system and watch what happens. But when nature performs this experiment for us, we can observe and learn. Every fragmentation event adds to our database, helps us refine our models, brings us closer to understanding the physical processes that shape these ancient objects. The data also revealed the limitations of our understanding. The non-gravitational forces affecting the comet's motion were difficult to model precisely. The mechanism of fragmentation remained uncertain. The original size and structure of the comet before fragmentation could only be estimated. These unknowns are not failures but opportunities, questions for future research, problems for the next generation of astronomers to solve. This is how science progresses, not in great leaps of perfect understanding, but in small steps of incremental knowledge. Each observation adds a piece to the puzzle. Each analysis refines our models. Each surprise forces us to reconsider our assumptions. The ghost of 3I Atlas in our data is one small contribution to this ongoing process, a few more bytes in the ever-growing database of human knowledge about the cosmos. As the fragments of 3I Atlas drifted beyond our ability to detect them, they didn't cease to exist. They continue their journey through the solar system, invisible to us, but still subject to the same physical laws, still following their orbits, still part of the cosmic clockwork. In a sense, they've returned to the state they were in for most of their existence, dark, cold, and unobserved. The brief period when they were visible to us was the exception, not the rule. This raises profound questions about the nature of knowledge and observation. Does something exist if we're not observing it? Of course it does. 3I Atlas existed for millennia before we detected it, and continues to exist now that we can no longer see it. But in another sense, its existence for us, its reality in human consciousness, was limited to those few weeks of observation. It emerged from the unknown, briefly entered our awareness, and then returned to the unknown. This transient nature of observation is particularly acute in astronomy. Unlike a biologist who can keep specimens, or a chemist who can repeat experiments, astronomers must accept that most of what they study is temporary and unrepeatable. We cannot ask 3I Atlas to return for another look. We cannot preserve a sample for future study. We have only the data we collected during its brief appearance, the ghost in our instruments, the pattern of numbers that encodes everything we'll ever know about this particular comet. Yet from these ephemeral observations, We can construct stories that span millions of years. We can imagine the comet's long journey from the Oort cloud, its ancient ice slowly approaching the sun. We can envision its previous passages, if there were any, and the changes it might have undergone. We can project forward to imagine the fate of its fragments spreading out along the orbit, perhaps to return individually in the far future. These stories are grounded in physics, constrained by observations, but they necessarily involve imagination and speculation. The data from 3i Atlas has been archived and will remain available for future researchers. Perhaps new analysis techniques will extract information we cannot currently perceive. Perhaps future observations of other comets will provide context that helps us better understand what we saw. Perhaps one day, advanced spacecraft will encounter the fragments of 3i Atlas in the outer solar system, providing direct measurements that confirm or refute our current understanding. This permanence of data alongside the impermanence of the phenomenon is another beautiful aspect of modern astronomy. Long after 3i Atlas has faded from memory, its ghost will persist in our databases. Future generations of astronomers with tools and knowledge we cannot imagine will be able to revisit these observations, to see what we saw, to perhaps understand what we could not. As we transition from contemplating the specific observations of 3i Atlas to imagining its deep history, we carry with us this sense of the fleeting nature of observation and the permanence of data. We've seen how patient observation and careful analysis allowed us to capture the ghost of this comet in our instruments. Now we'll journey backward in time, far beyond the reach of any observation, to imagine what the world was like when this comet last visited, if indeed it did. We'll explore the Earth of 12,000 years ago, a world of ice and change, of emerging humanity and dying megafauna, and wonder if eyes looked up at the night sky and saw the same visitor we've just bid farewell to. The data gives us the present and hints at the trajectory, but it's imagination, grounded in science, that lets us paint the full picture. We're about to travel from the realm of measurement to the realm of informed speculation, from what we know to what we can reasonably wonder about. The ghost in the data becomes a thread connecting us to the deep past, a bridge across millennia, a reminder that the cosmos operates on timescales that dwarf human history yet include it, embrace it, and give it context. The journey backward through time begins now, as we leave behind the precise measurements and digital data of the present and venture into the mists of deep history. Close your eyes for a moment and imagine the Earth rotating backward, the days reversing, the seasons flowing in reverse, years peeling away like pages in a book being rapidly turned backward. The cities disappear, the lights go out, the roads fade away, forests advance and retreat. Ice sheets pulse like breathing lungs, coastlines shift and change. We're travelling back 12,000 years, to a world that was both exactly the same and utterly different from the one we know. The Earth of 10,000 BCE was in the midst of profound transformation. The last glacial maximum, the peak of the most recent ice age, had occurred about 8,000 years earlier, and the planet was still emerging from its icy grip. Massive ice sheets, kilometers thick in places, were retreating from North America and Europe, but they still covered vast areas that are temperate today. Sea levels were perhaps 60 meters lower than present, exposing land bridges that connected continents. Britain was joined to Europe, Asia to America across what is now the Bering Strait, and countless islands were part of larger land masses. This was the world of the Younger Dryas, a period of dramatic climate fluctuation that saw rapid warming interrupted by sudden returns to near-glacial conditions. These changes weren't gradual shifts playing out over millennia, but sometimes dramatic transformations that occurred within human lifetimes. Imagine the confusion and wonder of people who saw forests die and be replaced by tundra, or who witnessed the opposite transformation, as cold-adapted plants gave way to warmth-loving species within a generation or two. The megafauna that had dominated the Pleistocene were in their final days. Mammoths still roamed the steppes of Siberia and the grasslands of North America, though their numbers were dwindling. Saber-toothed cats, giant ground sloths, cave bears, and dire wolves still existed, but they too were facing extinction. The causes are still debated: climate change, human hunting, disease, or more likely a combination of all these factors, but the result was clear. The world was losing its giants, and smaller, more adaptable species were inheriting the Earth. And what of humanity? We were there, of course, but in numbers so small that the entire global population was probably less than 10 million souls. We had spread to every continent except Antarctica, following game, seeking new territories, adapting to environments from tropical rainforest to Arctic tundra. We were still exclusively hunter-gatherers, though in some favoured locations, particularly in the Fertile Crescent of the Middle East, people were beginning to experiment with the cultivation of wild grains, taking the first tentative steps toward agriculture. These were fully modern humans, with brains as capable as our own, with language, art, music, and complex social structures. They had the same capacity for wonder, the same curiosity about the world, the same tendency to look up at the night sky and ask questions. They had mythologies and cosmologies, creation stories and explanations for the lights that moved across the heavens. They tracked the phases of the moon, noted the seasonal progression of constellations, and almost certainly recognized that some lights, the planets, wandered against the fixed stellar background. If Three-Eye Atlas appeared in their skies 12,000 years ago, what would they have seen? Without telescopes, they would only have noticed it if it became bright enough to be visible to the naked eye, which would require it to develop a substantial coma and perhaps a tail as it approached the sun. It would have appeared first as a fuzzy star, perhaps noticed by the keen-eyed observers who served as their community's sky watchers. Over weeks it would have brightened and moved across the sky, its fuzzy appearance becoming more pronounced, perhaps developing the classic tail that points away from the sun. Different cultures would have interpreted this apparition in different ways. To some, it might have been an omen, a message from the gods or ancestors. To others, it might have been a spirit travelling across the sky, or a celestial animal, or a tool wielded by divine beings. The specific interpretations are lost to us, but we know from historical records of more recent comets that they were rarely ignored. They were events that demanded explanation, that were woven into the mythological fabric of societies, that were remembered in oral traditions for generations. Consider what it would have been like to observe a comet without any understanding of what it actually was. You're a hunter on the grasslands of what is now Ukraine, following the herds of horses and reindeer that your people depend on for survival. You know the night sky intimately. It's your calendar, your clock, your navigation system. You know where each bright star should be at each season, which constellations herald the coming of spring or the approach of winter. And then, one night, there's something new, a fuzzy star where no star should be. You watch it night after night. It moves, slowly but perceptibly, against the stellar background. It brightens gradually, and then you notice something even stranger, a faint luminous streak extending from it, like smoke from a distant fire, but perfectly straight and always pointing away from where the sun set. Your people gather to discuss this apparition. The elders consult their memories, trying to recall if anything like this has been seen before. Stories are told, explanations are offered, rituals are performed. The comet becomes part of your world for those weeks or months. Children are born under its light and are thought to be specially marked. Important decisions are postponed or accelerated based on its appearance. Hunters might see it as a guide, leading them to new hunting grounds. Others might see it as a warning, urging preparation for hard times ahead. The comet becomes woven into the fabric of daily life, a cosmic presence that reminds everyone that the universe is larger and more mysterious than the familiar round of days and seasons. And then, gradually, it fades. The tail shortens and disappears. The fuzzy star grows dimmer, night by night, until one evening it's simply gone, returned to whatever realm it came from. But the memory remains. Stories are told around fires for years, decades, generations. The comet becomes part of the oral history, its appearance linked to whatever significant events happen to coincide with it. A particularly harsh winter, a successful hunt, the death of a leader, the discovery of new lands. Over time, the stories change, details are added or forgotten. The comet might transform from a celestial visitor to a mythological being, its astronomical nature completely obscured by layers of narrative and meaning. By the time writing is invented, thousands of years later, the original observation is unrecognizable, transformed into myth, perhaps preserved as a dragon in the sky, a cosmic serpent, a chariot of the gods, or any of the myriad ways human cultures have conceptualized celestial phenomena. This is the tragedy and beauty of deep history. We know our ancestors observed the skies with attention and reverence, but their observations are almost entirely lost to us. They saw comets, eclipses, meteor showers, supernova, all the cosmic phenomena that we observe with our modern instruments. But they could only preserve their observations in memory and story, media that transform and fade with time. The sky of 12,000 years ago was the same sky we see tonight, but the human experience of that sky, the meanings and stories attached to it, are irretrievably lost. Yet we can make educated guesses about what that world was like, based on archaeological evidence and our understanding of climate and ecology. The retreat of the ice sheets had opened up vast new territories for human habitation. In North America, the Clovis culture was spreading across the continent, their distinctive spear points found from Alaska to Mexico. These were sophisticated hunters, capable of taking down mammoths and other megafauna, but also adaptable enough to exploit a wide range of resources from small game to plants. In Europe, the Magdalenian culture was giving way to the Azilian, as the reindeer herds that had been the mainstay of the economy moved north following the retreating ice. People were adapting to forested environments, developing new tools and techniques for hunting, forest game like deer and wild boar. They were also beginning to exploit marine resources more intensively, as rising sea levels brought the coastline closer to many settlements. In the Middle East, the Natufian culture was emerging, a sedentary or semi-sedentary society that built permanent structures and intensively harvested wild cereals. They had sickles for harvesting grain, grinding stones for processing it, and storage facilities for keeping surplus. They were on the very brink of the agricultural revolution, perhaps just centuries away from the domestication of wheat and barley that would transform human society forever. In East Asia, people were adapting to the changing environments of the post-glacial world in their own ways. In Japan, the Jomon culture was beginning to develop, creating some of the world's earliest pottery. In China, people were exploiting the rich resources of the Yellow and Yangtze river valleys, gathering wild rice and millet, hunting deer and wild pig, and perhaps beginning to tend and protect useful plants in ways that would eventually lead to domestication. Each of these cultures had their own relationship with the sky, their own cosmologies and calendars, their own interpretations of celestial events. A comet appearing in 10,000 BCE would have been observed by thousands of distinct cultural groups, each with their own language, beliefs, and traditions. It would have meant different things to different people, been incorporated into different stories, been remembered or forgotten according to different cultural practices. The physical environment these people inhabited was also dramatically different from today. The Sahara, now the world's largest desert, was green and dotted with lakes. Hippos and crocodiles lived where now there is only sand. The Amazon rainforest was smaller, broken up by patches of savanna. The Great Lakes of North America were still forming as the ice sheets retreated, their water levels fluctuating wildly as different drainage routes opened and closed. The climate was unstable, prone to sudden shifts that could transform landscapes within decades. The Younger Dryas event, a sudden return to near-glacial conditions that occurred around 12 to 1800 years ago, and lasted for about 200 years, had recently ended. Temperatures had risen dramatically, perhaps by 10 degrees Celsius in just a few decades in some regions. This rapid warming was melting ice sheets, raising sea levels, changing ocean currents, and transforming ecosystems on a global scale. In this world of change and instability, a comet might have seemed like just another sign of the times, another indication that the old order was passing away and something new was emerging. Or it might have been seen as a cause of the changes, a celestial messenger bringing transformation to the earthly realm. We can never know for certain, but we can be confident that it would not have passed unnoticed or unremarked. The question of whether Thruway Atlas actually appeared 12,000 years ago remains open. The orbital calculations are uncertain, especially when extended so far into the past. Small errors in our measurements of its current trajectory, combined with the unknown effects of non-gravitational forces and planetary perturbations over millennia, mean we cannot be certain of its previous passages. It might have last appeared 11,000 years ago, or 13,000, or perhaps this was its first approach to the inner solar system in much longer, but the exact timing is less important than the connection it represents. Whether or not this specific comet appeared to our ancestors, comets certainly did. The sky they watched was populated by the same wanderers we observe today, following the same physical laws, tracing similar paths through the heavens. When we observe a comet today, we're participating in an ancient human tradition, one that stretches back to the very origins of our species. We're seeing what they saw, wondering what they wondered, feeling perhaps the same mix of awe and curiosity that they felt. The development of agriculture, which began shortly after our hypothetical 12,000-year-ago comet appearance, fundamentally changed humanity's relationship with the sky. Farmers needed to know when to plant and when to harvest, and the sky provided the most reliable calendar. The heliacal rising of certain stars, the phases of the moon, the position of the sun at different times of year, all became crucial information for agricultural societies. Astronomy became a practical necessity, not just a source of wonder. This agricultural revolution was not a single event, but a process that played out independently in different parts of the world over thousands of years. In each region, people domesticated different plants and animals, developed different agricultural techniques, and created different social structures to manage agricultural production and distribution. But in all cases, the result was the same: larger, denser populations, permanent settlements, social stratification, and the emergence of complex societies. If we imagine our comet returning every 12,000 years, its last appearance would have been at the very beginning of this transformation. It would have been seen by the last fully nomadic hunter-gatherers and the first tentative farmers. Its next appearance, 12,000 years from now, will be seen by whatever humanity has become, perhaps a spacefaring civilization, perhaps something unimaginably different, or perhaps nothing at all. The comet, if it exists on this schedule, brackets the entire history of civilization, from its earliest beginnings to its unknown future. The memory of that ancient world is preserved not in written records, but in our genes, in the archaeological record, and in the proxy records of climate stored in ice cores, ocean sediments, and tree rings. We can read the story of climate change in the layers of ice drilled from Greenland and Antarctica, each layer representing a year's snowfall, preserving information about temperature, atmospheric composition, and even volcanic eruptions and forest fires. We can trace the migrations of human populations through genetic analysis, following the paths our ancestors took as they spread across the globe. These scientific techniques allow us to peer into the deep past with a clarity that would have seemed magical to earlier generations. We can determine what plants grew in a particular region thousands of years ago by analyzing preserved pollen. We can reconstruct the diet of ancient peoples by studying isotopes in their bones. We can even extract and sequence DNA from fossils, revealing the genetic relationships between extinct species and their modern descendants. Yet for all our scientific tools, there's something irreducibly mysterious about the deep past. We can know the facts, the temperatures, the sea levels, the species present, but we cannot truly know the experience. What was it like to live in a world where humans were not the dominant species, where nature was truly wild, where the night sky was unpolluted by artificial light? What was it like to see a comet without knowing what it was? To witness this celestial visitor with no context except myth and wonder? These are questions that science cannot fully answer, but they're questions worth contemplating. They connect us to our ancestors not through data but through shared humanity. When we look at a comet today, even with all our scientific understanding, we still feel wonder. We still feel small in the face of cosmic phenomena. We still search for meaning in the patterns of the heavens. In this emotional and spiritual response, we're not so different from those ancestors who watched the same sky 12,000 years ago. The ice ages that shaped the world of 12,000 years ago were themselves cosmic phenomena, caused by variations in Earth's orbit known as Milankovitch cycles. The eccentricity of Earth's orbit, the tilt of its axis, and the precession of the equinoxes all vary on timescales of thousands to hundreds of thousands of years. These variations change the amount and distribution of solar energy reaching Earth's surface, triggering feedback mechanisms that can plunge the planet into ice ages or pull it out of them. This is another example of the cosmic clockwork we explored earlier, but operating on yet another timescale. The same gravitational forces that guide comets on their orbits also cause subtle variations in Earth's orbit, which in turn drive climate changes that shape the evolution of life and the course of human history. We're not separate from the cosmos. We're embedded in it, affected by it, shaped by it at every scale from the molecular to the planetary. The world of 12,000 years ago was also a world of rapid evolution and adaptation. The dramatic environmental changes of the post-glacial period created new ecological niches and destroyed others. Species that could adapt quickly thrived. Those that couldn't went extinct. This process of adaptation wasn't just biological but cultural. Human societies that could adjust to changing conditions, that could exploit new resources and develop new technologies were the ones that survived and spread. The domestication of plants and animals was perhaps the most significant adaptation of all. It was a mutual process. Humans changed the species they domesticated, but those species also changed human society. The need to tend crops and guard herds led to sedentary life. Sedentary life led to permanent structures, food storage, and population growth. Population growth led to social complexity, division of labor, and eventually to cities, writing, and all the hallmarks of civilization. In a sense, the agricultural revolution was humanity's response to the end of the Ice Age. The stable, warm climate of the Holocene, the geological epoch that began about 11,700 years ago and continues today, provided the conditions necessary for agriculture to develop and spread. Without this climatic stability, it's doubtful that complex civilizations could have emerged. We are children of the interglacial, products of a brief warm period between ice ages. And what of the future? If the natural cycles continue, another ice age will eventually come, though perhaps not for thousands of years. But human activity has now become a geological force in its own right, warming the planet through greenhouse gas emissions, potentially disrupting the natural cycles that have governed climate for millions of years. We have become players in the cosmic clockwork, not just observers, but participants who can alter the mechanisms we're only beginning to understand. This brings us back to our comet, our hypothetical 12,000-year visitor. If it returns in 12,000 years, what world will it find? Will the Earth still be habitable? Will humans still exist? Will we have spread to other planets, other star systems? Will we have developed technologies that allow us to visit the comet, rather than simply observing it from afar? Or will we have disappeared, leaving only ruins and mysteries for some other intelligence to puzzle over? These questions might seem abstract, irrelevant to our daily lives, but they're actually profound and immediate. They force us to think about our place in time, our responsibility to future generations, our role as temporary custodians of a planet that existed long before us and will exist long after us. The comet, in its patient orbit, reminds us that we are not the end point of history, but a chapter in an ongoing story. As we contemplate these vast spans of time, it's natural to feel a kind of vertigo, a disorientation at the sheer scale of it all. Our lives, which feel so full and significant to us, are barely blips in cosmic time. Entire civilizations rise and fall in what, to the comet, is just a single orbit. All of human history, all our achievements and failures, all our loves and losses, compress into a moment from the comet's perspective. But rather than making us feel insignificant, this perspective can be liberating. It puts our problems in context, reminds us that our current concerns, however pressing they seem, are temporary. It connects us to the grand sweep of cosmic evolution, makes us part of something magnificent and ongoing. We are the universe's way of knowing itself, of appreciating its own beauty, of wondering at its own mystery. In our brief moment of consciousness, we have the privilege of awareness, the gift of wonder, the capacity to appreciate the vastness in which we find ourselves. The Earth of 12,000 years ago was a world in transition, poised between the Ice Age and the modern era, between the age of hunter-gatherers and the age of farmers, between nature and civilization. If a comet appeared in that ancient sky, it would have been witnessed by humans at a crucial turning point in our species' history. It would have been a cosmic punctuation mark at the end of one chapter and the beginning of another. Now, as we prepare to journey even deeper into the cosmic context, to explore the vast and mysterious Oort cloud from which our comet might have come, we carry with us this sense of deep time, this connection to our ancestors, this awareness of our place in the ongoing story. The past is not dead. It lives on in us, in our genes, in our cultures, in our curiosity about the sky. And the future is not determined. It's being written now, by us, in how we choose to understand and interact with the cosmos of which we are part. The transition from the ancient Earth to the distant reaches of the solar system is like stepping from a familiar room into the vast night. We leave behind the warm, living world we know and venture into the cold, silent spaces where comets dwell. Yet even in that apparent emptiness, there is structure, history, and a kind of frozen beauty that speaks to the deep processes that shaped our solar system. We're about to explore one of the most mysterious regions of our cosmic neighborhood, a place that exists more in mathematical models than in direct observation, a spherical shell of ice and possibility that surrounds our solar system like a cosmic cocoon. Imagine traveling outward from the Sun, past the orbit of Earth, past Mars with its rusty deserts, past the asteroid belt with its tumbling rocks, past Jupiter with its swirling storms, past Saturn with its magnificent rings, past Uranus and Neptune, those ice giants in the outer darkness. Keep going. The Sun shrinks to a bright star, then to merely the brightest star. The familiar planets are lost in the glare behind you. You're entering the realm of the Kuiper Belt, where Pluto and its kin orbit in the freezing dark. But keep going still, past the Kuiper Belt, past the scattered disk, past the heliopause where the solar wind finally gives way to the interstellar medium. Keep going until the Sun is just another star among many, until you're 1,000 times farther from the Sun than Earth is, then 2,000 times, then 5,000 times. Now you're entering the Oort cloud, though you wouldn't know it by looking around. There are no signs, no boundaries, no sudden change in the appearance of space. The Oort cloud is not dense like a terrestrial cloud. It's a vast sparse sphere of icy bodies, so thinly distributed that even here, in what we call a cloud, you could travel for millions of kilometers without encountering a single object larger than a grain of sand. If you were standing on one of the Oort cloud comets, the nearest neighbor might be as far away as Earth is from Saturn. This is isolation beyond human comprehension. loneliness made manifest in cosmic architecture. The Oort cloud is thought to extend from about 2,000 astronomical units from the Sun to perhaps 100,000 astronomical units, nearly 2 light years. At these distances, the Sun's gravity is barely a whisper, just strong enough to keep these icy bodies bound to our solar system, but so weak that passing stars can easily perturb them. The cloud is spherical, unlike the disc-shaped Kuiper belt, because the orbits of its members have been randomized over billions of years by stellar encounters and galactic tides. It's a fossil, a preserved remnant of the early solar system, a library of ice that has been circulating in the dark for longer than Earth has existed. We have never directly observed an object in the Oort cloud. It's too far away, the object's too small and dark. We infer its existence from the comets that occasionally fall inward, their orbits suggesting an origin in this distant sphere. It's a scientific hypothesis, a necessary explanation for observed phenomena, a mathematical ghost that must exist for our models to make sense. Yet we speak of it with confidence, map its probable structure, estimate its population. This is the power of scientific inference, the ability to know the unseeable through the careful analysis of its effects. The Oort cloud is named after Jan Oort, the Dutch astronomer who first proposed its existence in 1950. Oort was trying to solve a puzzle. Why do we still see comets? Comets lose material every time they pass near the Sun. After a few thousand passages, they should be completely depleted. Yet we see fresh comets regularly, objects that appear to be approaching the Sun for the first time. Where do they come from? Oort's answer was elegant. There must be a vast reservoir of comets at the edge of the solar system, occasionally sending new ones inward when their orbits are disturbed. The formation of the Oort cloud takes us back to the birth of the solar system, 4.6 billion years ago. In the beginning, there was a nebula, a vast cloud of gas and dust probably enriched with heavy elements from one or more nearby supernova. Something, perhaps the shock wave from another supernova, perhaps gravitational instabilities, perhaps the tidal forces from a passing star, caused this nebula to begin collapsing. As it collapsed, it began to rotate, and as it rotated, it flattened into a disk. At the center, where the density was highest, the proto-sun began to form. In the disk surrounding the young sun, particles of dust began to stick together, forming larger and larger aggregates. These planetesimals, as they're called, continue to grow through accretion, sweeping up material in their orbital paths. In the inner solar system, where temperatures were high, only rocky materials could condense, leading to the formation of the terrestrial planets. But beyond the frost line, the distance from the Sun where water ice could remain solid, ices could also condense, allowing much larger bodies to form. The giant planets, Jupiter, Saturn, Uranus, and Neptune, grew massive enough to gravitationally dominate their regions of the disk. They swept up or ejected most of the remaining planetesimals in their vicinity. Many of these ejected bodies were flung outward, into highly elliptical orbits that took them far from the Sun. Over millions of years, perturbations from passing stars and the galactic tides circularized these orbits at vast distances, creating the spherical shell we call the Oort cloud. This process was violent and chaotic. For every comet now peacefully orbiting in the Oort cloud, many others were ejected from the solar system entirely, sent on hyperbolic trajectories into interstellar space. The early solar system was a gravitational shooting gallery, with planetesimals careening off the giant planets like pinballs, their fates determined by the precise angles and velocities of their encounters. It's estimated that the Oort cloud contains only a few % of the mass that was originally in the outer solar system. The rest was lost to interstellar space or fell into the Sun. The Oort cloud, then, is not a planned structure, but an emergent one, a natural consequence of planetary formation and dynamics. It's the solar system's attic, where old things are stored and forgotten until something disturbs them. Each comet in the Oort cloud is a time capsule, preserving the conditions of the early solar system in its frozen ice. When one falls inward and becomes visible to us, we're seeing material that has been in deep freeze for billions of years, unaltered by the heat and radiation that have transformed bodies in the inner solar system. The population of the Oort cloud is uncertain, but estimates suggest it contains trillions of objects larger than a kilometre across, with a combined mass several times that of Earth. These objects are primarily ice, water ice, but also frozen methane, ammonia, carbon dioxide and other volatiles. Mixed with the ice are dust and rocky materials, the non-volatile components that remain when a comet's ice sublimates. Each comet is unique in its exact composition, reflecting the local conditions where it formed in the protoplanetary disk. The ice in these comets is not like the ice in your freezer. At the temperatures of the Oort cloud just a few degrees above absolute zero, ice becomes a rock-hard solid, stronger than concrete. It can maintain structural integrity even in bodies kilometers across. But this same ice becomes unstable when heated, sublimating directly from solid to gas when exposed to solar radiation. This is what creates the spectacular comas and tails of comets, the sudden phase transition of materials that have been solid for billions of years. Life in the Oort cloud, if we can call it life, is almost perfectly static. With no sunlight to drive weather, no geology to reshape surfaces, no chemistry beyond the slowest of reactions, Oort cloud objects exist in a state of suspended animation. A day on an Oort cloud comet might last months or years, not that it matters, since there's no sunrise or sunset, just eternal night punctuated by the faint light of distant stars. The sun, from the Oort cloud, would be visible but not special, just another star among thousands visible to the naked eye, if eyes existed there to see. Yet this apparent stasis hides a slow, patient dynamics. Oort cloud objects are not fixed in their orbits, but constantly perturbed by external forces. Every few million years, a star passes within a few light years of the sun, its gravity tugging on the Oort cloud, changing orbits, sometimes sending comets falling inward. The entire solar system oscillates up and down through the galactic plane with a period of about 60 million years, subjecting the Oort cloud to varying tidal forces. Even the combined gravity of the galactic disk and bulge exerts a subtle influence, slowly reshaping the cloud over billions of years. These perturbations are usually tiny, changing a comet's orbit by just a small amount. But occasionally the perturbation is just right to send a comet falling toward the sun. The journey inward takes millions of years. For most of that time, the comet remains frozen and invisible. Only in the final approach, when it enters the inner solar system, does it warm enough to become active, to develop the coma and tail that make it visible to us. It's like a creature awakening from the longest hibernation imaginable, suddenly thrust into light and warmth after eons of cold and darkness. The idea that 3I Atlas might be on a 12,000-year orbit suggests it's not a typical Oort cloud comet on its first approach, but something intermediate, perhaps a comet that has made several passages, its orbit gradually modified by planetary encounters, or perhaps a Kuiper belt object that was scattered outward and is now returning. The exact classification matters less than the connection it represents between the inner and outer solar system, between the warm realm of planets and the cold realm of comets. The Oort cloud is not unique to our solar system. Other stars almost certainly have their own comet clouds, formed through similar processes. In fact, we may occasionally exchange comets with other star systems. When stars pass close to each other, they can trade Oort cloud objects, or send them on trajectories that will eventually encounter other stars. Some of the comets in our Oort cloud might have formed around other stars billions of years ago, and some of the comets that formed in our solar system might now be orbiting other stars, or travelling through interstellar space. This raises fascinating possibilities. Could comets carry organic molecules, or even primitive life from one star system to another? This idea, called panspermia, is controversial but not impossible. We know that some bacteria can survive in space-like conditions, and the interior of a comet might provide protection from radiation during the long interstellar journey. If life exists elsewhere in the galaxy, comets could be one mechanism for its spread. Every comet that enters our solar system could potentially be carrying passengers, microscopic hitchhikers from another world. Even without invoking life, comets are carriers of complex chemistry. The organic molecules detected in comets, amino acids, sugars, and other prebiotic compounds, might have been important for the origin of life on Earth. The early Earth was bombarded by comets and asteroids, delivering water and organic molecules that could have jump-started the chemical evolution that led to life. In this view, we are all children of comets, our very existence dependent on these icy messengers from the outer darkness. The Oort cloud also represents a kind of boundary, a transition zone between our solar system and interstellar space. Inside the cloud, objects are bound to our sun, part of our cosmic family. Outside, they belong to the galaxy at large, wanderers in the vast spaces between stars. The edge of the Oort cloud is sometimes considered the true boundary of the solar system, the limit of the sun's gravitational influence. Beyond this, we enter the realm of other stars, other systems, other stories. But boundaries in space are never sharp lines. They're gradual transitions, zones of decreasing influence rather than walls or borders. The Oort cloud itself gradually thins with distance from the sun, its outer edge defined more by our definitions than by any physical discontinuity. Some comets probably orbit in the fuzzy boundary region, sometimes bound to our sun, sometimes not, depending on the perturbations they experience. These marginal objects remind us that categories and classifications are human constructs imposed on a universe that operates on continua. As we contemplate the Oort cloud, we're really contemplating the architecture of our solar system, the way its components are arranged and why. The neat, orderly arrangement of planets gives way to the scattered disorder of the Kuiper belt, which gives way to the spherical symmetry of the Oort cloud, which gives way to the emptiness of interstellar space. Each zone has its own character, its own population of objects, its own dynamics. Together, they form a system of stunning complexity and beauty, a gravitational symphony played out over billions of years. The patience required to study such a system is profound. We observe comets for a few months or years as they pass through the inner solar system, then extrapolate their behavior over millions of years. We build computer models that simulate billions of years of orbital evolution in hours or days of processing time. We piece together the history of the solar system from fragments of evidence, meteorites, lunar samples, comet spectra, like detectives reconstructing a crime that happened before Earth existed. This is the remarkable thing about astronomy. We can know so much about places we've never been, objects we've never touched, events we've never witnessed. Through the careful application of physics, mathematics, and observation, we can map the invisible Oort cloud, trace the journey of comets across millions of years, understand processes that occur on scales far beyond human experience. We can sit on our small planet and comprehend the vast system of which we're part. The Oort cloud is often described as pristine, unaltered since the formation of the solar system. But this is only partially true. While the bulk composition of Oort cloud comets probably reflects the original nebula, their surfaces have been processed by billions of years of cosmic ray bombardment. This radiation creates a dark, organic, rich crust on the surface of comets, a kind of space weathering that changes their appearance and properties. When a comet becomes active, this crust cracks and peels away, revealing the pristine ice beneath. This process of surface modification and renewal is another kind of clock, another way the universe marks time. The depth of radiation damage on a comet's surface tells us how long it has been exposed to cosmic rays. The rate at which the crust forms and breaks away tells us about the comet's activity history. Even in the apparent stasis of the Oort cloud, time leaves its marks, change accumulates, history is written in ice and dust. The study of the Oort cloud is also a study in inference and imagination. Since we cannot observe it directly, we must deduce its properties from the comets that visit us. It's like trying to understand a forest by examining the occasional leaf that blows into your yard. We build models, make predictions, and wait for new comets to test our ideas. Each new long-period comet is a messenger from the Oort cloud, carrying information about conditions in that distant realm. The fragmentation of 3I Atlas adds another layer to this story. If the comet broke apart due to thermal stress or tidal forces, it tells us something about the structural integrity of Oort cloud objects. Perhaps they're not solid bodies but loosely bound aggregates, rubble piles, held together by weak gravity and ice. This would make sense given their formation history. Gentle accumulation in the cold outer disk rather than violent collisions that would create more solid bodies. The fragments of 3I Atlas are now heading back to the outer solar system, each on its own modified orbit. Some might return to the Oort cloud, rejoining the vast reservoir of comets. Others might be on escape trajectories, destined to leave the solar system entirely. Still others might be on shorter orbits, destined to return to the inner solar system in thousands rather than millions of years. The fragmentation event has multiplied the comet's legacy, creating multiple messengers where there was one. This multiplication of objects through fragmentation is another process that shapes the Oort cloud over time. Every comet that breaks apart creates multiple smaller comets, increasing the number of objects but decreasing their average size. Over billions of years, this process, along with erosion from repeated passages near the Sun, gradually depletes the cloud. The Oort cloud we see today, or rather infer today, is probably smaller and less massive than it was in the early solar system. It's a depleting resource, a reservoir slowly draining over cosmic time. Yet even as it depletes, the Oort cloud continues to surprise us. The discovery of long-period comets with unusual compositions or orbits challenges our models and forces us to refine our understanding. Each new comet is a test of our theories, a check on our assumptions. The Oort cloud, invisible and distant as it is, keeps us honest, reminds us that there's always more to learn, always another mystery to explore. As we think about the Oort cloud as the source of our hypothetical returning comet, we're really thinking about cycles and reservoirs, about the long-term stability of the solar system, about the connections between its innermost and outermost regions. The Oort cloud is like a savings account of the early solar system, preserving material from the beginning, occasionally making withdrawals in the form of comets. Each comet that visits us is spending capital that was saved 4.6 billion years ago. The embrace of the Oort cloud is gentle but persistent. Objects orbit there for billions of years, held by the faintest touch of the sun's gravity. They're barely bound, easily perturbed, always on the edge of escape. Yet most remain, circling in the darkness, patient and eternal. They're like meditation masters, demonstrating the art of stillness, the beauty of patience, the power of persistence. They show us that not all existence needs to be active, dynamic, changing. Sometimes just being, just continuing, just maintaining orbit is enough. The philosophical implications of the Oort cloud are as vast as its physical extent. It shows us that our solar system is not a closed box but an open system, exchanging material with interstellar space. It demonstrates that the formation of planetary systems is not a neat, efficient process, but a messy, wasteful one that scatters more material than it collects. It reminds us that the cosmos operates on timescales that dwarf human experience, that patience is not just a virtue, but a cosmic principle. As we prepare to contemplate the deeper meanings of these vast cycles, to explore what it might mean for a comet to serve as a bridge across millennia, we carry with us this image of the Oort cloud, vast, dark, patient, and full of potential. Every comet sleeping in that distant sphere is a story waiting to be told, a journey waiting to begin, a connection waiting to be made between the cold outer darkness and the warm inner light. The Oort cloud embraces our entire solar system, and through the comets it sends us. It embraces us too, connecting us to the deepest history and the most distant reaches of our cosmic home. Now we turn from the physical to the philosophical, from the mechanical to the meaningful. What does it mean for an object to travel for 12,000 years to serve as a physical link between epochs so different that they might as well be different worlds? We're about to explore the idea of the comet not just as a chunk of ice and rock, but as a messenger, a time capsule, a thread connecting points in history that otherwise have no connection. This is where science gives way to poetry, where fact yields to metaphor, where the comet becomes not just an object, but a symbol of continuity in a universe of constant change. Consider what a message is at its most fundamental level. It's information that travels from a sender to a receiver, across some distance in space or time. Usually we think of messages as intentional, words spoken or written, signals broadcast, meanings encoded deliberately for communication. But nature sends messages too, unintentional ones, in the form of light from distant stars, fossils in ancient rocks, DNA passed from parent to child. These natural messages carry information about their origins, their history, their journey. They don't mean to communicate, but they do anyway, to anyone capable of receiving and interpreting their signals. A comet is such a natural message, written in ice and dust, sent from the early solar system to the present, from the cold outer darkness to the warm inner light. The message is not in words but in chemistry, in isotope ratios, in mineral compositions, in orbital elements. Every molecule in the comet tells part of the story, where it formed, what conditions were like, what processes it has undergone. Scientists reading this message learn about the solar system's formation, about the distribution of elements, about the processes that shape planetary systems. But if we allow ourselves to think more poetically, more metaphorically, the comet carries other kinds of messages too. It's a reminder of deep time, of cycles that transcend human experience. It's a demonstration of persistence, of the power of patient waiting. It's a connection to our ancestors who saw comets in their skies and wondered what they meant. It's a bridge to future generations who will see comets we'll never see, who will wonder the same things we wonder, who will be part of the same ongoing conversation between humanity and the cosmos. The idea of a 12,000-year cycle adds another dimension to this message. If 3i Atlas really does return on this schedule, then each appearance is like a chapter in an ongoing story. The comet sees, if we can anthropomorphize for a moment, the Earth change dramatically between visits. Ice ages come and go. Species evolve and go extinct. Continents drift, mountains rise and erode, rivers change course. And in the most recent chapter, a species of clever apes develops technology, builds civilizations, and begins to understand the cosmos. From the comet's perspective, if it had one, humanity's rise would be sudden and shocking. On one visit, there are only scattered bands of hunter-gatherers, living much as their ancestors had for hundreds of thousands of years. On the next visit, there are cities, satellites, space probes, a technological civilization that has transformed the planet. It would be like leaving a caterpillar and returning to find a butterfly, a transformation so complete that the connection to the earlier form is almost unrecognizable. This temporal perspective reminds us that change is the norm, not the exception. We tend to think of our world as stable, permanent, the way things have always been and will always be. But the comet's long absence and return shows us that everything changes, given enough time. Mountains that seem eternal are temporary bumps that will be worn flat. Oceans that seem permanent are temporary accumulations of water that will eventually evaporate or be subducted. Even the continents, those seeming foundations of geography, drift and collide and break apart over hundreds of millions of years. Yet within this constant change, there are continuities. The laws of physics that govern the comet's orbit remain the same. The atoms that make up its ice are the same atoms that existed at the beginning of the universe, reshuffled and rearranged, but fundamentally unchanged. The genetic code that governs life on Earth has been passed down, with modifications for billions of years. Change and continuity are not opposites, but partners, dancing together through time. The comet serves as a kind of cosmic metronome, marking out a rhythm against which we can measure other changes. If it returns every 12,000 years, it divides history into comet periods, epochs defined not by human events, but by celestial ones. The last comet period saw the rise of agriculture and civilization. The one before that saw the emergence of modern humans as the dominant species. The next one will see what? We cannot know, but we can wonder, and in wondering, we connect ourselves to that future, make ourselves part of the ongoing story. Messages across millennia don't have to be intentional to be meaningful. The comet doesn't mean to tell us about the early solar system, but it does. It doesn't mean to connect us to our ancestors and descendants, but it does. It doesn't mean to make us contemplate our place in the universe, but it does. Meaning arises from the intersection of the message and the receiver, from our ability to interpret, to find significance, to create narrative from observation. This is one of the unique capabilities of consciousness, the ability to find meaning in the meaningless, to create significance where none was intended. A comet is just a ball of ice and rock following the laws of physics. But to us, it can be an omen, a wonder, a scientific opportunity, a philosophical prompt. We project meaning onto the universe, and in doing so, we make it meaningful. We are the universe's meaning makers, the ones who transform raw phenomena into significance. The message of the comet changes depending on who receives it, and when. To ancient astronomers, comets were messages from the gods, warnings or promises written in the sky. To medieval scholars, they were atmospheric phenomena, exhalations of the earth rising to the heavens. To Enlightenment scientists, they were proof of the clockwork universe, following predictable paths governed by mathematical laws. To modern astronomers, they're samples of the early solar system, carrying information about our origins. Each interpretation is valid within its context, each one revealing as much about the interpreters as about the comet itself. We see in the comet what we're prepared to see, understand from it what we're capable of understanding. As our knowledge grows, so does the depth and complexity of the message we receive. The comet hasn't changed, but our ability to read its message has evolved dramatically. If we think of the comet as carrying a message across 12,000 years, we might ask, what message would we want to send across such a span? If we could encode information in an object that would be delivered to humanity 12,000 years from now, what would we say? Would we warn them about mistakes to avoid? Would we share our greatest achievements? Would we simply say, we were here, we wondered about you, we hope you're well? These are not idle questions. We actually face this challenge with our space probes, particularly those leaving the solar system. The Voyager spacecraft carry golden records with sounds and images from Earth, messages for any intelligence that might find them millions of years from now. The Pioneer plaques show the location of our solar system and basic information about humans. These are our attempts to send messages across vast spans of time and space, to communicate with unknown receivers in an uncertain future. But perhaps the most important messages are the unintentional ones, the ones we send simply by existing and acting. Every piece of space debris we leave in orbit is a message about our technology and our carelessness. Every extinct species is a message about our impact on the biosphere. Every scientific discovery we make and record is a message about our curiosity and intelligence. We're constantly writing messages to the future, whether we mean to or not. The comet reminds us that these messages will be received and interpreted by intelligences we cannot imagine, in contexts we cannot predict. Just as we puzzle over the meaning of ancient monuments, trying to understand what our ancestors meant to communicate, future beings will puzzle over our artifacts, our ruins, our modifications to the planet. They will read messages in our geology, the sudden appearance of plastics in the sediment, the spike in radioactive isotopes from nuclear testing, the mass extinction event we're currently causing. But the comet also carries a more hopeful message, that some things endure. Despite all the changes, all the chaos, all the uncertainty, the comet continues its orbit. It demonstrates that persistence is possible, that cycles can continue across vast spans of time, that there are some constants in a universe of variables. This is a comforting message, a reassurance that not everything is ephemeral, that some connections can span millennia. The very fact that we can predict the comet's return, if it does return on a 12,000-year cycle, is a kind of message from the past to the future. Newton's laws, Kepler's equations, our understanding of orbital mechanics, these are messages from dead scientists to living ones and through us to future ones. The knowledge accumulates, passes from generation to generation, allows us to make predictions that span far longer than any human lifetime. We stand on the shoulders of giants, as Newton said, and future generations will stand on ours. In this view, science itself is a message across millennia, a gradually accumulating body of knowledge that connects all of humanity across time. Every observation, every calculation, every theory adds to this message. The work done by astronomers tracking 3I Atlas becomes part of this grand communication, data that will be available to future scientists we'll never meet, contributing to understandings we'll never see. The fragmentation of 3I Atlas adds poignancy to this message metaphor. The single messenger has become multiple messengers, each carrying part of the original message, but also creating new messages through their divergent paths. It's like a story that splits into multiple versions, each one evolving differently, creating a family of related but distinct narratives. Future observers might see one fragment and not others, receiving only part of the message, having to infer the whole from the part. This fragmentation also reminds us that messages can be corrupted, degraded, lost in transmission. Not everything that is sent is received. Not everything that is received is understood. The universe is full of noise, interference, confusion. Messages are missed, misinterpreted, forgotten. The comet that our ancestors might have seen 12,000 years ago left no decipherable record in human memory. If it carried a message, we failed to receive it, or at least failed to preserve it in a form we can now recognize. Yet perhaps the message is preserved in other ways. Perhaps the dust from that ancient comet fell to Earth and became part of the soil, was absorbed by plants, eaten by animals, incorporated into the bodies of our ancestors and eventually into us. Perhaps we carry in our very atoms a message from that ancient visitor, a physical connection we're unaware of but that exists nonetheless. We're all made of star stuff, as Carl Sagan said, but we're also made of comet stuff, asteroid stuff, the accumulated debris of the solar system's history. The message of the comet is also about humility. It reminds us that we are not the center of the universe, not the purpose of creation, not the endpoint of evolution. We are temporary arrangements of matter that have briefly achieved consciousness, allowing us to perceive and interpret messages from the cosmos. The comet was here before us and will be here after us. Its message will outlast any message we create. Its journey will continue long after our journey ends. But rather than making us feel insignificant, this can make us feel connected. We are part of the message, part of the ongoing story. Every time we observe a comet, we add ourselves to its history. Every time we calculate an orbit, we project ourselves into its future. We become part of the cosmic narrative, characters in a story that began before us and will continue after us but includes us in an essential way. The philosophical implications of a message across millennia extend to questions of purpose and meaning. If the universe is sending us messages in the form of comets and other celestial phenomena, what is it trying to tell us? Of course, this assumes intentionality where none exists. The universe is not trying to tell us anything. But the human mind seeks meaning, finds patterns, creates narratives. We can't help but interpret, to find significance, to imagine purpose. Perhaps the message is simply, you're not alone. Not in the sense of extraterrestrial intelligence, though that remains a possibility, but in the sense of being part of a vast, interconnected system. Every comet connects us to the outer solar system. Every meteorite connects us to asteroids. Every photon of sunlight connects us to the sun. Every atom in our bodies connects us to ancient stars. We are not isolated individuals on an isolated planet, but part of a vast web of matter and energy, space and time. Or perhaps the message is pay attention. The universe is full of wonders, full of mysteries, full of beauty, but we have to look up to see them. The comet appears in our sky uninvited, demanding nothing, offering only itself as an object of contemplation. It's an invitation to wonder, to curiosity, to awe. It breaks us out of our terrestrial concerns, reminds us that there's a vast cosmos beyond our immediate experience. The message might also be about time itself, about the nature of existence in a temporal universe. The comet demonstrates that the past persists into the present, that the future is being determined now, that all moments are connected in the great flow of time. It shows us that patience is not just waiting, but a form of travel, a way of moving through time at the rate of 1 second per second, 1 year per year, 1 millennium per millennium. As we contemplate these messages across millennia, we're really contemplating the nature of existence itself. What does it mean to be a conscious being in a universe of mostly unconscious matter? What does it mean to perceive patterns and meaning in phenomena that have no inherent meaning? What does it mean to be temporary witnesses to processes that operate on timescales far beyond our experience? These are questions without definitive answers, questions that each generation must grapple with anew. The comet doesn't answer them for us, but it provides a focal point for our contemplation, a concrete object around which our abstract thoughts can crystallize. It's a philosophical prompt delivered by orbital mechanics, a meditation trigger launched from the Oort cloud. As we prepare to look toward the future, to imagine what the world might be like when the comet returns, we carry with us this sense of the comet as messenger, as bridge, as connection across vast spans of time. Whether the message is physical, encoded in molecules and orbits, or metaphorical, arising from our interpretation and imagination, it connects us to the grand sweep of cosmic history. We are receivers of ancient messages and senders of future ones, links in a chain of communication that stretches from the Big Bang to the heat death of the universe. The transition from message to future is natural. Every message implies a future receiver. Every communication assumes continued existence. As we turn our thoughts to what might come, we're not abandoning the present or the past, but extending their trajectory, following the comet's path not just through space, but through time, imagining the world that might witness its next return. Now let us turn our gaze forward, not backward, and imagine what eyes might witness the comet's return 12,000 years from now. This is not an exercise in prediction. No one can truly know what the future holds, but rather an invitation to wonder, to stretch our imagination across the same vast span of time that separates us from our Ice Age ancestors. As you lie there, breathing softly in the darkness, allow your mind to drift forward through time, carried on the same patient orbit that might bring our cosmic visitor back to the inner solar system in that unimaginably distant epoch. The future is a strange country, one we can never visit, but one that we're constantly creating through our actions in the present. Every choice we make, every path we take, every discovery we achieve, or disaster we cause ripples forward through time, shaping the world that will exist when the comet returns. We are not just observers of history, but active participants in its creation, and the future that will greet the comet's next appearance is being written now, in our time, by our hands. Consider first the multiple possible futures that spread out before us like branches of an infinite tree. In one branch, humanity continues its expansion into space, and by the time the comet returns, we have become a true spacefaring civilization. The solar system is alive with human activity. Cities on Mars, mining operations in the asteroid belt, scientific stations on the moons of Jupiter and Saturn, perhaps even expeditions to the Oort cloud itself. In this future, the returning comet is not merely observed from Earth but visited directly, sampled, perhaps even altered in its course or composition. We don't wait for cosmic visitors to come to us, we go out to meet them. Imagine spacecraft powered by technologies we can barely conceive of today, matching velocities with the comet while it's still in the outer solar system. Scientists, or whatever humans have become by then, land on its surface, drill into its ancient ice, set up laboratories to study its composition in situ. The comet becomes not just an object of observation but a destination, a research station, perhaps even a source of resources for the sprawling human civilization that has spread throughout the solar system. The mystery that we can only glimpse from afar today becomes an open book, its secrets laid bare by direct investigation. In this optimistic future, the technologies that seem like magic to us now have become commonplace. Fusion power has given us unlimited clean energy. Artificial intelligence has solved problems we couldn't even formulate. Biotechnology has extended human lifespans indefinitely, cured all diseases, perhaps even allowed us to adapt our bodies for life in space or on other worlds. The humans who greet the comet's return might be as different from us as we are from our hunter-gatherer ancestors, transformed by technologies that emerge from discoveries we're only beginning to make today. But there are other branches, other possible futures, and not all of them are so bright. In another timeline, humanity faces challenges we couldn't overcome. Climate change, resource depletion, war, pandemic, or some combination of disasters reduces our civilization to ruins. The great cities are abandoned, their skyscrapers slowly crumbling as nature reclaims them. The satellites that circle Earth have long since fallen from orbit, burning up in the atmosphere or crashing into the oceans. The vast network of information that we call the internet exists only as corroded servers in flooded data centers, its contents as lost as the Library of Alexandria. In this darker future, humanity hasn't disappeared. We're too adaptable, too widespread for that. But we've lost much of what we built. The survivors, perhaps numbering in the millions rather than billions, have reverted to simpler ways of life. They farm with hand tools, travel by foot or beast, live in small communities that rarely contact each other. They have legends of the time before, when humans flew through the air and spoke across vast distances. But these stories seem like myths, too fantastic to be believed. When the comet appears in their sky, they see it as their distant ancestors did, as an omen, a mystery, a wonder that they lack the tools to understand. Yet even in this diminished future, the appearance of the comet might spark something. Perhaps it reminds them of the old stories, the tales of when humans knew the names and paths of celestial objects. Perhaps it inspires them to begin observing more carefully, to start the long climb back to scientific understanding. The comet becomes a catalyst for renaissance, a reminder that there is more to existence than mere survival, that the universe holds mysteries worth investigating even when life is hard. Between these extremes lie countless intermediate futures, each one a unique mixture of advancement and setback, triumph and tragedy. Perhaps we develop incredible technologies but lose our humanity in the process, becoming something cold and mechanical, efficient but joyless. Perhaps we solve our material problems but face new psychological or spiritual crises we can't anticipate. Perhaps we fragment into multiple species, some staying on Earth, others adapting to life in space, each group evolving in different directions until they can barely recognize each other as related. In one particularly intriguing possibility, humanity has merged with its technology to such a degree that the distinction between natural and artificial no longer makes sense. Our descendants might exist primarily as information patterns in vast computer networks, experiencing reality through simulations, able to adjust their subjective time so that the comet's 12,000-year orbit seems like days or stretched out to seem like millions of years. They might observe the comet not through telescopes but through direct sensory interfaces, with a network of sensors spread throughout the solar system, experiencing its approach from multiple perspectives simultaneously. Or perhaps by then we've made contact with other intelligences, either from elsewhere in our galaxy or arising from our own artificial intelligence research. The comet's return might be witnessed not just by humans, but by a community of diverse minds, biological, artificial, and perhaps forms we can't even imagine. Each type of intelligence might perceive and interpret the comet differently, creating a rich tapestry of understanding that no single species could achieve alone. The comet becomes a shared experience that helps unite these different forms of consciousness, a common point of reference in a universe of radical diversity. Consider too the possibility that we've discovered ways to manipulate space and time that seem impossible from our current understanding of physics. Perhaps we've learned to create stable wormholes, allowing instantaneous travel across vast distances. The comet's long journey from the Oort cloud might seem quaint, a relic of the era when everything had to travel through normal space at subliminal speeds. Our descendants might view the comet's patient orbit the way we view a horse-drawn carriage, charming, historical, but utterly obsolete as a means of transportation. Or perhaps we've discovered that consciousness can exist independently of physical form, that what we call the soul or mind can be transferred, transmitted, duplicated. Death might have become optional, a choice, rather than an inevitability. The humans who witnessed the comet's return might include individuals who saw its previous appearance, who have lived for 12,000 years, accumulating experience and wisdom we can barely imagine. To them, the comet's cycle might not seem so long, just another recurring event in their vastly extended lives. But perhaps the most profound change will be in our relationship with time itself. We currently experience time as a flowing river, carrying us inevitably from past to future. But physics suggests that time might not be as simple as our perception suggests. Perhaps our descendants will have learned to perceive time differently, to see past, present, and future as equally real, equally accessible. They might experience the comet's entire orbit simultaneously, seeing it as a static four-dimensional structure rather than a moving object. The question, when will it return, might become meaningless to minds that don't experience when the way we do. The Earth itself will have changed by the time the comet returns, regardless of what humanity does. 12,000 years of geological processes will have reshaped the landscape in subtle but measurable ways. Rivers will have carved their valleys deeper. Coastlines will have shifted. Some volcanoes will have erupted while others will have gone extinct. The Earth's magnetic field might have weakened, strengthened, or even reversed. The continents will have moved, not much, perhaps a few hundred meters, but enough to be detectable. The climate, even without human influence, will have shifted through natural cycles. We might be heading into or emerging from another ice age, depending on the complex interplay of orbital cycles, solar activity, and atmospheric composition. The forests, deserts, and grasslands will have migrated, following the shifting patterns of temperature and precipitation. Species will have evolved, adapted, gone extinct, been replaced by new forms. The biosphere is never static, always changing, always experimenting with new solutions to the challenge of existence. Even the night sky will have changed. 12,000 years of stellar motion will have altered the constellations, not dramatically, but enough to be noticeable. Some of the stars we see today will have exhausted their fuel and died, perhaps exploding as supernovae, perhaps fading to white dwarfs. New stars will have been born from nebulae, adding their light to the celestial tapestry. The comet will return to a sky that is familiar but not identical, changed in ways that reflect the dynamic nature of our galaxy. The moon will be slightly farther from Earth, continuing its slow spiral outward that has been proceeding since its formation. Days will be imperceptibly longer as Earth's rotation continues to slow due to tidal friction. These changes are tiny on human timescales but accumulate over millennia. The world the comet returns to will be different in myriad small ways that add up to significant change. If humanity survives and thrives, we might by then have developed technologies to predict and even prevent cosmic catastrophes. The asteroid impacts that have periodically devastated Earth's biosphere might have become preventable. Asteroids nudged into safe orbits or mined for resources. Solar flares might be predicted and shielded against. Supervolcanic eruptions might be prevented or controlled. We might have become masters of our own fate, no longer subject to the random catastrophes that have punctuated Earth's history. Or we might have learned that control is an illusion, that the universe is fundamentally unpredictable, chaotic in ways that no amount of technology can overcome. We might have developed a philosophy of acceptance, of riding the waves of change rather than trying to control them. The comet's return might be seen as a reminder of this fundamental unpredictability, a symbol of the forces beyond our control that shape our existence. The future might hold discoveries that completely revolutionize our understanding of reality. Perhaps we'll discover that our universe is just one of infinitely many, that what we call reality is just a tiny slice of a much larger multiverse. Perhaps we'll find that consciousness is fundamental to the universe, not an emergent property, but a basic feature like mass or charge. Perhaps we'll discover that time travel is possible, that cause and effect are not as simple as they seem, that the future can influence the past in ways we're only beginning to glimpse in quantum mechanics. Any of these discoveries would profoundly change how we interpret the comet's journey. It might not be a simple elliptical orbit through space, but a complex path through multiple dimensions. Its 12,000-year period might be just one aspect of a more complex cycle, involving parallel universes or higher dimensions. What seems like a simple astronomical phenomenon from our current perspective might be revealed as something far more mysterious and profound. The possibility of extraterrestrial life adds another dimension to our speculation about the future. By the time the comet returns, we might have discovered that life is common in the universe, that every star system harbors some form of biology, or we might have discovered that we are utterly alone, the only consciousness in a vast empty cosmos. Either discovery would profoundly affect how we see ourselves and our place in the universe. If we've made contact with alien civilizations, the comet's return might be a shared observation, compared with similar phenomena in other star systems. We might learn that long-period comets are common throughout the galaxy, that every civilization watches these patient travelers and wonders about their significance. Or we might discover that our solar system is unusual, that long-period comets are rare, that we're privileged to witness such phenomena. The comet itself might be transformed by then. If humanity has spread throughout the solar system, we might have altered the comet's orbit, perhaps capturing it into a shorter period to study it more easily, or perhaps sending it on a new trajectory entirely. We might have mined it for resources, using its water for spacecraft fuel, its organic compounds for biological processes. The comet that returns might bear the marks of human intervention, no longer a pristine messenger from the early solar system, but a modified object that tells the story of human expansion into space. Or perhaps we'll have developed an ethic of non-interference, choosing to observe without altering, to study without disturbing. The comet might be protected, designated as a cosmic heritage site, preserved in its natural state for future generations to observe and wonder at. This would represent a maturity in our relationship with the cosmos, a recognition that not everything needs to be exploited, that some things have value simply in existing, in continuing their ancient cycles undisturbed. The social structures of humanity in 12,000 years are impossible to predict. We might have achieved a global unity, a single civilization that encompasses Earth and its offspring colonies throughout the solar system. Or we might have fragmented into thousands of distinct societies, each with its own culture, technology, and way of life. We might have transcended the need for government, achieving a form of organization we can't currently imagine. Or we might have developed forms of control and coordination that would seem dystopian to us now. The economy of the future, if such a thing still exists, might be based on principles we haven't discovered yet. Perhaps matter and energy are so abundant that scarcity no longer exists, and the economy is based on information, creativity, or experiences. Perhaps we've discovered new forms of value we can't currently conceive of. The comet might be valuable not for its material resources, but for its historical significance, its scientific information, its aesthetic beauty, or qualities we don't yet have words for. Language itself will have evolved dramatically by the time the comet returns. English, if it survives at all, will be as different from today's English as our language is from Proto-Indo-European. New languages will have emerged, perhaps designed rather than evolved, optimized for communication between different types of minds, or for expressing concepts we haven't yet discovered. The comet might be described in languages that can express nuances of meaning impossible in our current linguistic frameworks. Art and culture will have gone through countless movements, revolutions and renaissances. Entirely new art forms will have been invented, perhaps involving senses we don't currently possess or dimensions we can't currently perceive. The comet might inspire artworks we couldn't understand, using media we haven't imagined, expressing emotions we haven't felt. Or perhaps art will have returned to simplicity, finding beauty in basic forms and fundamental experiences, and the comet will be celebrated in ways that would be familiar to any human from any era. Religion and philosophy will have evolved to incorporate discoveries and experiences we can't anticipate. New spiritual movements will have arisen and fallen, each one trying to make sense of humanity's place in an ever-expanding, ever more complex universe. The comet might be incorporated into future mythologies, seen as a divine messenger, a cosmic clock set by a creator, or a random event in a meaningless universe, depending on the philosophical frameworks of the time. The very concept of humanity might have changed by then. We currently define ourselves in biological terms, Homo sapiens, a particular species of primate. But if we merge with our technology, if we genetically modify ourselves, if we upload our consciousness to artificial substrates, what does it mean to be human? The beings that observe the comet's return might consider themselves our descendants, even if they share no DNA with us, if they maintain continuity of culture and consciousness rather than biology. Death itself might have a different meaning in that distant future. If consciousness can be backed up, copied, restored, is death even possible? Or does it become a choice, a transition rather than an ending? The beings who witnessed the comet's return might include some who chose to sleep through the intervening millennia, waking specifically to observe this event. Others might have lived every moment, accumulating 12,000 years of experience, becoming something we would barely recognize as once human. The educational system of the future, if formal education still exists, will have to deal with an exponentially larger body of knowledge. How do you teach history when there's 12,000 more years of it? How do you teach science when the fundamental theories have been revised dozens of times? Perhaps knowledge is directly downloadable, or perhaps the focus shifts from knowing facts to knowing how to think, how to learn, how to adapt. The comet might be used as a teaching tool, a concrete example that connects different eras, different scientific theories, different ways of understanding the universe. The challenges facing humanity in that distant future will likely be ones we can't imagine. Just as our ancestors couldn't have anticipated climate change, nuclear weapons, or artificial intelligence, we can't anticipate the problems our descendants will face. Perhaps they'll be dealing with the heat death of the universe, trying to extract energy from black holes as the last stars fade. Perhaps they'll be negotiating with alien civilizations for resources or territory. Perhaps they'll be trying to prevent their artificial intelligences from evolving beyond their control, or trying to maintain their humanity in a world where enhancement and modification are the norm. Yet some challenges might be eternal. The need for meaning, for purpose, for connection. These might persist regardless of technological advancement. The beings who watch the comet return might struggle with the same existential questions we do. Why are we here? What is the purpose of existence? How should we live? The comet in its patient orbit might serve as a reminder that some questions don't have answers, that mystery is a permanent feature of existence, not a temporary problem to be solved. The comet's return might coincide with other significant events in that future era. Perhaps it arrives just as humanity is preparing for its first journey to another star. Perhaps it appears during a crisis that threatens civilization, becoming a symbol of hope or despair depending on the outcome. Perhaps its arrival marks the beginning or end of an era, a punctuation mark in the long sentence of human history. These coincidences would be chance, of course, but humans are meaning-making creatures, and we would inevitably weave the comet into whatever narrative we're telling ourselves at the time. The science of that era will have advanced in ways we can barely imagine. Perhaps we'll have a theory of everything, a complete understanding of how the universe works from the quantum to the cosmic scale. Perhaps we'll have discovered that our universe is a simulation, or that consciousness creates reality, or that time is an illusion. The comet might be understood not just as a ball of ice and rock, but as a node in a vast network of quantum entanglement, or a manifestation of higher dimensional geometry, or something even stranger. Yet for all these possibilities, perhaps the most likely future is one we haven't imagined, one that would surprise us as much as our world would surprise our ancestors. The future has a way of confounding predictions, of taking unexpected turns, of being simultaneously better and worse than we expect, but almost never what we expect. The comet will return to a world shaped by countless decisions, discoveries, disasters, and triumphs that we cannot foresee. As you lie there in the darkness, breathing slowly, imagine yourself as a bridge between the deep past and the deep future. You exist at a particular moment in the comet's cycle, should it truly return every 12,000 years. You are equidistant from its last visit and its next, standing at the midpoint of its orbit. The ancestors who might have seen it are as far behind you as the descendants who might see it are ahead. You are the fulcrum on which past and future balance, the present moment through which the comet's trajectory passes. This perspective can bring a profound sense of peace. Your individual concerns, while real and valid, are part of a much larger flow. The problems that seem overwhelming will pass. The joys that seem fleeting are no less real for their brevity. You are part of an ongoing process, a link in a chain that stretches from the formation of the solar system to its eventual end. The comet, if it follows this grand cycle, has seen countless moments like this one. Countless beings wondering about their place in the cosmos, and it will see countless more. The future's faint glimmer, the possibility of the comet's return, is both a promise and a question. It promises that the cycles continue, that the universe persists, that there will be a future even if we can't know what it holds, and it asks us what kind of future we want to create, what kind of world we want the comet to return to, what message we want to send forward to those who will watch its next approach. As we prepare to turn our attention to the patience required to study such vast cycles, to the scientific endeavor that allows us to peer across such enormous spans of time, we carry with us this vision of possible futures, this spectrum of what might be. The comet's hypothetical return in 12,000 years is not just an astronomical event, but a milestone, a marker that makes us think about where we've been and where we're going. It's a gentle reminder that the future is not fixed but fluid, not determined but determinable, shaped by countless actions and decisions, including our own. The science of patience begins with a simple recognition. The universe operates on its own schedule, not ours. As you continue to rest there in the quiet darkness, you're breathing slow and steady. Consider what it means to study phenomena that unfold over timescales that dwarf human experience. Astronomy is perhaps the ultimate exercise in patience, a discipline where practitioners routinely work on questions they know they'll never see answered, gather data for future generations to analyze, and build instruments for discoveries they won't live to witness. Think about what it means to be an astronomer studying long-period comets. You might observe a comet for a few months as it passes through the inner solar system, then calculate that it won't return for thousands of years. You publish your observations, knowing that no one alive will be able to verify your orbital calculations through direct observation of the comet's return. You're essentially writing a message to scientists who won't be born for millennia, saying we saw this object, we measured its path, we predict it will return on this date. Please check our work. This is an act of profound faith, not religious faith, but faith in the continuity of human civilization, in the persistence of scientific inquiry, in the value of knowledge for its own sake. It's a belief that someone, somewhere, somewhen, will care about these observations, will find value in these measurements, will continue the work you've begun. Every astronomer who studies long-period comets is participating in a multi-generational project that transcends individual lives, careers, even civilizations. The instruments we build to study the cosmos embody this patience in physical form. The great observatories, both ground-based and space-based, are designed to last for decades, to be upgraded and maintained by successive generations of scientists. The Hubble Space Telescope has been observing for over 30 years. Serviced by astronauts, its instruments upgraded, its mission extended far beyond its original planned lifetime. The scientists who now use Hubble include many who weren't born when it was launched. They inherit not just the telescope, but the decades of observations it has made, the vast archive of data that documents how the universe has changed over those 30 years. Future telescopes are being planned that won't see first light for decades. Scientists spend entire careers designing instruments they might never use, solving technical problems for observations they won't make. They are planting trees whose shade they'll never enjoy, building foundations for discoveries that will be made by their students. This is the patience of science, not passive waiting, but active preparation for a future that will arrive in its own time. The data we collect today will outlive us all. Every observation of 3i Atlas, every spectrum, every image has been digitized and archived. Barring civilizational collapse, this data will be available to researchers centuries from now. They'll be able to reanalyze it with techniques we haven't invented, extract information we don't know how to see, answer questions we haven't thought to ask. We are not just observing for ourselves, but for all future astronomers, creating a permanent record that transcends our temporary existence. This accumulation of data over time is what makes astronomy possible. We can study stellar evolution, even though stars live for millions or billions of years, because we observe many stars at different stages of their lives. We can understand galactic dynamics, even though galaxies rotate over hundreds of millions of years, because we observe thousands of galaxies at different angles and distances. We assemble a picture of slow processes by observing many examples frozen at different moments, like understanding a movie by examining individual frames. The patient accumulation of observations also reveals changes we wouldn't otherwise notice. Variable stars were discovered because astronomers carefully recorded stellar brightnesses for many years. The expansion of the universe was discovered because astronomers measured galactic distances and velocities over decades. The acceleration of cosmic expansion, one of the most surprising discoveries in modern cosmology, required comparing observations separated by years. Without patience, without long-term monitoring, these discoveries would have been impossible. Consider the search for exoplanets, planets orbiting other stars. The first confirmed detection was in 1992, but the search had been ongoing for decades before that. Astronomers knew that planets must exist around other stars. It would be bizarre if our solar system were unique, but finding them required instruments of extraordinary precision and years of patient observation. Now we know of thousands of exoplanets, and we're beginning to characterize their atmospheres to search for signs of habitability or even life. This transformation from ignorance to knowledge took less than a human lifetime, but it required the patient work of thousands of scientists over decades. The study of climate change is another example of the science of patience. We can see Earth's climate changing because we have records stretching back decades, centuries, even millennia if we include proxy data from ice cores and tree rings. Without these long-term records, climate change would be invisible, hidden in the noise of year-to-year weather variation. It's only by patiently collecting data over long periods that we can see the trends, identify the causes, and predict future changes. Patience in science isn't just about waiting. It's about maintaining consistency over long periods. Measurements must be made the same way year after year, decade after decade to be comparable. Instruments must be calibrated against stable standards. Definitions and units must be preserved. This requires not just individual patience but institutional patience. The commitment of entire organizations to long-term projects that outlast individual careers. The Voyager missions exemplify this institutional patience. Launched in 1977, they're still operating, still sending back data from interstellar space. The scientists who designed these missions knew they would take years to reach Jupiter and Saturn, decades to reach Uranus and Neptune, and decades more to reach the edge of the solar system. Many of the original team members have retired or died, replaced by younger scientists who inherited not just the spacecraft, but the responsibility for their operation. The Voyagers will continue traveling through space for millions of years, long after they've stopped transmitting, carrying their golden records as messages to whoever might find them in the unimaginably distant future. This brings us to an interesting paradox. Astronomy requires patience, but it also compresses time. Through telescopes, we see events that happened millions or billions of years ago happening right now from our perspective. We watch stars explode in distant galaxies, seeing in a few weeks a process that actually occurred when dinosaurs roamed Earth. We observe the cosmic microwave background, seeing the universe as it was 380,000 years after the Big Bang, compressed into maps we can examine at our leisure. We are time travelers, but we can only travel into the past and only as observers, never as participants. The light from 3 Atlas that we observed had traveled for minutes to reach us, a tiny delay by cosmic standards, but still a form of time travel. We were seeing the comet not as it was, but as it had been. If it had suddenly vanished, we wouldn't have known for several minutes. This delay becomes more pronounced with distance. When we observe the nearest star, Proxima Centauri, we're seeing it as it was 4.2 years ago. When we observe the Andromeda Galaxy, we're seeing it as it was 2.5 million years ago. The universe we observe is not the universe as it is, but the universe as it was, with different parts seen at different times in their history. This temporal complexity requires a special kind of thinking. Astronomers must mentally reconstruct the actual sequence of events from observations that arrive out of order. A supernova in a distant galaxy might be observed before one in a nearer galaxy, even though the distant one actually occurred millions of years earlier. We see the universe not as a snapshot, but as a collage of different times, a temporal mosaic that we must interpret carefully to understand the true history of cosmic events. Patience is also required in the development of theories. It took centuries to go from the first telescopic observations to our modern understanding of the cosmos. Each generation of scientists built on the work of their predecessors, adding new observations, refining theories, correcting errors. The heliocentric model, the laws of planetary motion, the theory of gravity, the discovery of other galaxies, the expansion of the universe, dark matter, dark energy. Each breakthrough required not just insight but patience, the slow accumulation of evidence until the truth became undeniable. Even today we're working on questions that might take generations to answer. What is dark matter? What is dark energy? Are there other universes? Is there life elsewhere? These questions won't be answered quickly or easily. They require new instruments, new observations, new theories, and most of all, patience. The scientists working on these questions know they might spend their entire careers without finding definitive answers. They're contributing to a collective effort that transcends individual ambition. The fragmentation of 3i Atlas reminds us that patience sometimes means accepting incomplete information. We observe the comet's breakup, but we'll never know exactly why it happened or what became of all the fragments. We must be patient with our ignorance, comfortable with uncertainty, willing to say, "We don't know," and wait for future observations that might provide answers. This is harder than it sounds. Humans naturally seek closure, want definitive answers, prefer certainty to ambiguity. Science requires us to resist these impulses, to remain open to new information, to hold our conclusions lightly. Patience also means being willing to be wrong. Scientific theories are provisional, always subject to revision based on new evidence. What we think we know about comets, about the solar system, about the universe, might be overturned by future discoveries. The patient scientist must be prepared for this, must even welcome it. Being proven wrong means we've learned something new, moved closer to truth. It requires humility and patience to build on foundations that might shift, to work within frameworks that might be superseded. The peer review process in science is itself an exercise in patience. Submitting a paper for publication means waiting months for reviewers to evaluate it, responding to their criticisms, revising and resubmitting, waiting again. A discovery made today might not be published for a year or more. This slow, careful process can be frustrating, but it ensures that published results have been scrutinized, that obvious errors have been caught, that the scientific record is as accurate as possible. It's a form of collective patience, the community taking time to verify claims before accepting them. Graduate students in astronomy embody the science of patience in their training. They spend years learning the background needed to contribute to research. They work on problems that might not yield results for years. They learn to operate instruments, analyze data, write code, all in service of questions that might take decades to answer fully. They are apprentices in patience, learning not just facts and techniques, but the mental discipline required for long-term scientific inquiry. The funding of science also requires patience, both from funders and researchers. Basic research might not yield practical applications for decades or ever. The knowledge gained from studying distant comets might seem useless from a practical standpoint, yet history shows that basic research often leads to unexpected applications. The study of atomic spectra seemed purely academic until it enabled the development of lasers. The study of quantum mechanics seemed abstract until it enabled the development of computers. Funders must be patient, supporting research without demanding immediate returns. Public communication of science requires its own form of patience. Explaining complex ideas to non-specialists takes time and care. Building public support for long-term projects requires sustained engagement. Scientists must be patient with misconceptions, willing to explain the same concepts repeatedly, finding new ways to make difficult ideas accessible. They must also be patient with the pace of public understanding, recognizing that it takes time for new discoveries to be absorbed into common knowledge. The search for extraterrestrial intelligence might be the ultimate expression of scientific patience. SETI researchers have been listening to the cosmos for decades, searching for signals that might indicate intelligent life elsewhere. They found nothing conclusive yet, but they continue listening, continue searching, continue refining their methods. They know that the galaxy is vast, that civilizations might be rare, that we might need to listen for centuries before detecting a signal. This is patience on a civilizational scale, a search that might outlast our species. Climate science requires us to be patient with processes that unfold over decades and centuries. We must make decisions today based on predictions of what will happen decades from now. We must ask current generations to make sacrifices for future generations they'll never meet. This requires a kind of collective patience, a willingness to act on long-term consequences rather than short-term benefits. It's a test of our species' ability to think and act on timescales longer than individual lives. The preservation of scientific data for future generations is an act of patience and faith. We store observations in formats we hope will be readable decades or centuries from now. We maintain archives that might not be accessed for years. We document our methods so future scientists can understand what we did. This is like planting a forest we'll never see mature, creating resources for scientists we'll never meet. As we observe the universe, we're also observing the effects of patience on cosmic scales. Mountains are worn down by erosion over millions of years. Continents drift apart at the speed fingernails grow. Stars fuse hydrogen into helium over billions of years. Galaxies collide and merge over hundreds of millions of years. The universe itself has been expanding for 13.8 billion years and will continue expanding for trillions more. Everything in nature demonstrates patience, the slow unfolding of processes according to physical laws. The hypothetical 12,000-year orbit of our comet is itself a lesson in patience. If it exists, it has been patiently following this path for millions of years, neither hurrying nor delaying, simply continuing according to the laws of physics. It doesn't care about human timescales, doesn't adjust its schedule for our convenience. It demonstrates a kind of cosmic patience that puts our human impatience in perspective. As individual humans, we struggle with patience. We want answers now, results now, gratification now. But as a species, as a scientific community, we're capable of remarkable patience. We build cathedrals that take centuries to complete. We maintain traditions that span millennia. We work on problems that won't be solved in our lifetimes. This collective patience is one of our species' greatest achievements, allowing us to accomplish things no individual could do alone. The digital age has in some ways made patience harder. We're used to instant communication, immediate access to information, rapid results. But it has also enabled new forms of patience. We can now collect and store vast amounts of data, waiting for the right analysis techniques to be developed. We can simulate billions of years of cosmic evolution in hours of computer time. We can coordinate observations across the globe, maintaining watch on variable phenomena continuously. Technology amplifies our patience, allowing us to observe longer, store more, and analyze deeper than ever before. Machine learning and artificial intelligence are beginning to transform astronomical research, but they too require patience. Training neural networks to identify patterns in astronomical data takes time. Validating their results requires careful comparison with known examples. We must be patient as we learn to trust these new tools, to understand their capabilities and limitations. They are not magic solutions, but new instruments that require patience to master. The patience required in science is not passive, but active. It's not just waiting, but preparing, observing, recording, analyzing. It's maintaining vigilance over long periods, being ready for rare events, keeping instruments calibrated and functional. It's the patience of a hunter waiting for prey, alert and ready, not the patience of a stone enduring erosion. Scientific patience is purposeful, directed towards specific goals even when those goals are distant. The collaborative nature of modern astronomy requires patience with other humans as well as with the cosmos. Large projects involve hundreds or thousands of scientists from dozens of countries. Coordinating such efforts requires patience with different working styles, different cultures, different priorities. Building consensus takes time. Resolving disagreements takes patience. The human element of science requires as much patience as the observational element. As we near the end of our contemplation of patience, consider how it connects to the earlier themes of our journey. The whisper of the comet required patience to detect and track. The cosmic clockwork operates with patient precision over billions of years. The ghost in the data will wait patiently in our archives for future analysis. The echoes of the past require patient reconstruction from fragmentary evidence. The Oort cloud embodies patience, holding comets in cold storage for eons. Messages across millennia require patience from both senders and receivers. The future's faint glimmer requires patience as we wait to see what unfolds. Patience ties all these themes together. It's the thread that connects past and future, the quality that allows us to perceive processes longer than our lives, the discipline that enables scientific progress. Without patience, we would be trapped in the present moment, unable to learn from the past or prepare for the future. Patience extends our reach across time, allowing us to participate in stories larger than ourselves. The comet, whether it returns in 12,000 years or not, has taught us about patience simply by existing. Its hypothetical orbit forces us to think on timescales that stretch our imagination. Its fragmentation reminds us that patience sometimes means accepting incomplete stories. Its journey from the Oort cloud demonstrates the patience of gravity, slowly pulling objects across billions of kilometers. Every aspect of the comet's story is a lesson in patience. As you lie there, breathing slowly, feeling the patient rhythm of your heartbeat, you're experiencing patience in its most fundamental form. Your body is patiently maintaining itself, cells dividing, proteins folding, neurons firing in patterns that create consciousness. You don't have to think about these processes. They continue patiently, whether you're aware of them or not. You're a collection of patient processes, a symphony of biological patience that allows you to exist, to think, to wonder about comets and cosmos. The transition from patience to mystery is natural. The universe's greatest mysteries are revealed only to those patient enough to observe carefully over long periods. As we prepare for our final contemplation, we carry with us this appreciation for patience, this recognition that the universe unfolds on its own schedule, revealing its secrets slowly to those willing to wait, to watch, to wonder without demanding immediate answers. And now we arrive at the heart of our contemplation, the unanswered question that has guided our entire journey through the night. As your breathing continues its gentle rhythm, as your mind floats in that peaceful space between waking and sleeping, we return to where we began, with a question that has no definitive answer, a mystery that invites wonder rather than demanding solution. What if 3i Atlas will return every 12,000 years? This question has carried us from the present moment back to the Ice Age, out to the Oort cloud, forward to an unimaginable future, and through the patient work of scientific discovery. Now we hold this question one final time, not to answer it but to appreciate it, to find peace in the not knowing. The beauty of an unanswered question is that it remains alive, dynamic, full of possibility. An answered question is closed, finished, filed away. But an unanswered question continues to generate thought, to inspire imagination, to motivate investigation. The question of the comet's return is particularly beautiful because it may never be definitively answered. Even if a comet appears in 12,000 years, we cannot be certain it's the same comet, the descendant of 3i Atlas, rather than a different long-period visitor. The question remains open, a permanent invitation to wonder. Science is often presented as being about answers, about facts, about certainty. And science does provide these things. We know the speed of light, the age of the universe, the structure of DNA, but at its heart, science is about questions, about curiosity, about the willingness to say, I don't know, but let's find out. Every answer in science generates new questions. Every discovery opens new mysteries. The island of knowledge expands, but so does the shoreline of ignorance. The more we know, the more we realize we don't know. This is not a failure of science, but its greatest triumph. A universe that could be completely understood, fully explained, definitively mapped, would be a small, boring universe. But our universe continues to surprise us, to confound our expectations, to reveal new layers of complexity and beauty. Dark matter and dark energy, discovered in just the last few decades, make up 95% of the universe, and we have no idea what they are. Quantum mechanics and general relativity, our two most successful theories, are fundamentally incompatible. Life's origin remains mysterious despite decades of research. Consciousness, the very thing that allows us to ask questions, remains largely unexplained. The mystery of 3i Atlas is tiny compared to these cosmic mysteries, but it's connected to them. The comet's composition might hold clues about the early solar system. Its orbit might tell us about stellar encounters in our galaxy's past. Its fragmentation might reveal something about the structure of primordial planetesimals. Every small mystery is a thread in the vast tapestry of cosmic mystery. Pull on one thread, and others move. Answer one question, and others appear. Living with mystery requires a certain comfort with uncertainty, a peace with not knowing. This is challenging in a culture that values answers, that rewards certainty, that treats "I don't know" as weakness rather than honesty. But uncertainty is not ignorance. It's an accurate assessment of our state of knowledge. We know some things with high confidence, other things with less confidence, and many things not at all. Being clear about these distinctions is crucial for both scientific progress and personal peace. The mystery of the comet's return also connects us to the mystery of our own existence. Why are we here? How did life begin? What is consciousness? What happens after death? These are questions that may never have definitive answers, but they're worth contemplating nonetheless. They connect us to every human who has ever lived, all of whom have wondered about these same mysteries. The comet, in its possible return, reminds us that we are temporary participants in an ongoing mystery that began before us and will continue after us. Consider how different cultures have related to cosmic mystery. Some have created elaborate mythologies to explain celestial phenomena. Others have developed philosophical systems that embrace mystery as fundamental. Still others have pursued scientific investigation to push back the boundaries of the unknown. All these approaches are valid responses to the mystery that surrounds us. They represent different ways of being human in a mysterious universe. The fragmentation of 3i Atlas adds layers to the mystery. Why did it break apart? Was it structurally weak from the beginning? Or did something happen during this particular passage? Will the fragments continue to fragment, creating a cascade of ever smaller pieces? Or will some fragments survive to return intact? Each question branches into more questions, creating a tree of mystery that could occupy astronomers for generations. Mystery is not the enemy of science, but its motivation. Without mystery, there would be no reason to investigate, no questions to answer, no discoveries to make. Mystery is the engine that drives scientific progress, is what gets astronomers out of bed for pre-dawn observations, what keeps them analyzing data late into the night, what motivates them to design new instruments and develop new theories. The day we run out of mysteries is the day science ends. But mystery serves other purposes beyond motivating investigation. It keeps us humble, reminding us that we don't have all the answers. It keeps us curious, maintaining our sense of wonder about the universe. It connects us to something larger than ourselves, something that transcends our individual lives and even our species. Mystery is a doorway to transcendence, a reminder that existence is bigger, stranger, and more wonderful than we can fully comprehend. The unanswered question of the comet's return places us in a particular position in time. We are after the observation but before the confirmation. We have seen something, measured it, wondered about it, but we cannot know for certain what it means. This is where most of science actually happens, in the space between observation and understanding, between data and theory, between question and answer. It's an uncomfortable space for those who want certainty, but it's a creative space for those who embrace mystery. Think about all the unanswered questions that surround us every day. Why does this person behave that way? What will the weather be next month? What will I be doing in 10 years? Life is full of mysteries, most of which we've learned to live with. We make plans despite uncertainty, form relationships despite not fully understanding other people, pursue goals despite not knowing if we'll achieve them. We're mystery-navigating beings, constantly operating with incomplete information. The cosmic mysteries simply extend this everyday mystery to larger scales. Just as we don't know what tomorrow will bring, we don't know what the universe will reveal tomorrow. Just as we don't fully understand ourselves, we don't fully understand the cosmos. The mystery is fractal. It exists at every scale, from the quantum to the cosmic, from the personal to the universal. We are mysteries to ourselves, living in a mysterious universe, and somehow we manage not just to survive, but to thrive. The question of Three-Eye Atlas's return also highlights the role of speculation in science. We cannot know for certain if it will return, but we can speculate based on available evidence. This speculation is not wild guessing, but informed imagination, constrained by physics, guided by observation. It's a creative act that generates hypotheses for future testing. Today's speculation becomes tomorrow's research program, next century's established fact or discarded error. Speculation about the comet's return connects us to broader speculations about the future. Will humanity survive? Will we spread to other planets? Will we discover extraterrestrial life? These questions cannot be answered with certainty, but they're worth considering. They shape our actions in the present, influence our priorities, guide our dreams. The mystery of the future is not a void, but a space of possibility, a canvas on which we paint our hopes and fears. The peaceful acceptance of mystery is different from passive resignation. It's an active choice to be comfortable with not knowing, to find beauty in questions as well as answers. It's recognizing that mystery is not a problem to be solved, but a fundamental aspect of existence. The universe is under no obligation to be comprehensible to human minds. The fact that we can understand as much as we do is remarkable. The fact that mysteries remain is not surprising but expected. As you lie there in the darkness, breathing gently, you are surrounded by mystery. The nature of consciousness that allows you to experience this moment is mysterious. The quantum processes occurring in every atom of your body are mysterious. The dark matter that passes through you undetected is mysterious. You are a mystery within mysteries, a question asking questions, a temporary arrangement of matter that has somehow become aware of itself and its cosmic context. The comet, in its journey through space, doesn't experience mystery. It simply follows its path, obeying physical laws without questioning them. Mystery requires consciousness, requires beings capable of wondering, of recognizing that there are things they don't know. We are the universe's mystery experiencers, the parts of cosmos that have developed the capacity to be puzzled by existence. Through us, the universe experiences its own mystery. This capacity for mystery might be one of humanity's defining characteristics. Other animals show curiosity, but as far as we know, only humans contemplate abstract mysteries, wonder about cosmic questions, create art and philosophy and science in response to the unknown. Our relationship with mystery is part of what makes us human. To lose our sense of mystery would be to lose something essential about ourselves. The mystery of Three-Eye Atlas is also a reminder that the universe still has surprises for us. Despite centuries of scientific progress, despite our sophisticated instruments and theories, a chunk of ice can still confound us, can still raise questions we cannot answer. This is humbling, but also exciting. It means there's still discovery to be done, still wonders to uncover, still mysteries to explore. The universe is not a solved problem, but an ongoing revelation. As our contemplation nears its end, consider how the mystery of the comet connects to the mysteries of your own life. What questions do you carry that may never be answered? What uncertainties do you live with every day? How do you find peace with not knowing? The comet's unanswered question is a cosmic version of the personal mysteries we all navigate. Learning to be at peace with cosmic mystery can help us be at peace with personal mystery. The comet's possible return in 12,000 years is a mystery that transcends individual lives. None of us will live to see if it returns. This places the mystery beyond personal concern, makes it a pure question without practical implications for our daily lives. We can wonder about it without needing to know the answer. This is the gift of cosmic mystery. It allows us to exercise our capacity for wonder without the pressure of needing resolution. In the end, the question, what if 3i Atlas will return every 12,000 years, is less important than the journey it has taken us on. We've travelled from the inner solar system to the Oort cloud, from the present to the deep past and distant future. We've contemplated time and space, patience and change, existence and meaning. The question has been our companion, our guide, our gentle prompt to wonder. Whether it has a definitive answer matters less than the thoughts it has inspired. As you continue to breathe slowly, to rest in the darkness, let the mystery of the comet merge with all the other mysteries that surround you. Let it be a reminder that you live in a universe full of wonders, full of questions, full of possibilities. You don't need to solve these mysteries, don't need to answer every question. You can simply appreciate them. Let them inspire wonder. Let them connect you to the vast, beautiful, mysterious cosmos of which you are part. The comet, if it exists on its hypothetical 12,000-year orbit, continues its journey whether we understand it or not. It doesn't need our comprehension to exist. It doesn't require our observation to continue. It simply is, following its path through the darkness, patient and persistent, a mystery moving through mystery. And we, in our brief moment of consciousness, have the privilege of wondering about it, of asking questions that may never be answered, of participating in the cosmic mystery through our capacity to be mystified. This is perhaps the deepest lesson of our contemplation, that mystery is not a barrier to understanding, but a doorway to wonder. The unanswered question of the comet's return doesn't close off possibilities, but opens them. It doesn't limit our thinking, but expands it. It doesn't frustrate our curiosity, but feeds it. The mystery is not a wall, but a horizon, always receding as we approach, always revealing new landscapes of possibility. And so, we return to silence, to darkness, to the quiet space where our journey began. The comet, whether real or imagined, whether returning or gone forever, has served its purpose. It has been our vehicle for contemplation, our prompt for wonder, our connection to the cosmos. The question of its return remains unanswered, and that's as it should be. Some questions are more valuable unanswered, more beautiful as mysteries than they would be as facts. In the vast darkness of space, countless comets follow their patient orbits. Each one a mystery, each one a story we'll never fully know. They don't announce themselves, don't demand attention, don't insist on being understood. They simply continue, quiet and persistent, following paths established billions of years ago, carrying their ancient ice through the darkness. They are reminders that the universe is larger than our knowledge, older than our history, more patient than our brief lives can comprehend. The specific mystery of 3i Atlas, will it return in 12,000 years, now dissolves into the larger mystery of existence itself. Why is there something rather than nothing? How did consciousness arise from unconscious matter? What is the ultimate fate of the universe? These questions dwarf our small comet's orbit, yet they're connected to it. Every specific mystery is a facet of the ultimate mystery. Every small question, an echo of the biggest questions. As sleep approaches, as your conscious mind prepares to yield to the mysterious realm of dreams, you can release the question of the comet's return. You don't need to hold on to it, don't need to solve it, don't need to worry about it. It will remain a mystery whether you ponder it or not. The universe will continue its patient unfolding whether you watch or sleep. The comet, if it exists on its long orbit, will continue its journey through the darkness, carrying its secrets, maintaining its mystery. Let the mystery be a lullaby, a gentle reminder that you don't need to understand everything, don't need to have all the answers, don't need to solve every puzzle. You can rest in not knowing, find peace in uncertainty, discover comfort in mystery. The universe has been mysterious for 13.8 billion years and will continue to be mysterious for trillions more. Your brief moment of consciousness is not required to solve its mysteries, but simply to appreciate them. To add your wonder to the sum of wonder that conscious beings have felt since consciousness began. The comet's dust, dispersed now through the solar system, drifts on solar winds and radiation pressure. Some of it will fall into the sun, adding its ancient substance to our star. Some will drift outward, perhaps leaving the solar system entirely. Some will encounter planets, moons, asteroids, adding tiny amounts of mass to these bodies, and some, just a few particles perhaps, will drift down through Earth's atmosphere, becoming shooting stars that someone, somewhere, will see and wonder about. That wonder is the comet's true legacy, not the answer to whether it will return, but the questions it raised, the thoughts it inspired, the connections it created between us and the cosmos. Every person who reads about Three-Eye Atlas, who sees an image of it, who wonders about its nature and fate, becomes part of its story. The comet has touched us across the vast distances of space, and we have touched it with our attention, our curiosity, our wonder. In this touch, brief and gentle as it was, we find meaning that transcends the physical. Yes, the comet was just ice and rock following orbital mechanics, but it was also a visitor, a messenger, a prompt for contemplation. It connected us to the deep past and distant future, to the outer reaches of our solar system, to the patient processes that shape our cosmic neighborhood. It reminded us that we are part of something vast and ancient and ongoing. The question of its return is now yours to carry, if you choose, or to release if you prefer. It can be a seed for future wonder, a gentle mystery to ponder on other quiet nights, or it can be a passing thought, appreciated and released, like the comet itself. There is no right way to relate to mystery, no correct response to unanswered questions. There is only your response, your relationship with the unknown, your peace or struggle with uncertainty. As the boundaries between waking and sleeping begin to blur, as your thoughts become less linear and more dreamlike, the comet can transform. It need not remain a scientific object bound by physics and chemistry. It can become mythic, poetic, symbolic. It can represent whatever you need it to represent. Patience, persistence, mystery, connection, cycles, returns. In dreams, the comet can speak, can carry messages, can bridge impossible distances. The mystery deepens and transforms, becoming personal, becoming yours. Tomorrow the sun will rise, Earth will continue its rotation, the moon will continue its orbit. The cosmic clockwork will tick forward another day. Somewhere in the outer darkness, the fragments of Three-Eye Atlas will be a few million kilometers farther from the sun, continuing their long journey to whatever destination awaits them. The universe will be one day older, one day changed, one day closer to futures we cannot imagine, and the mystery will remain, patient and eternal, waiting for wonder. But for now, in this moment, you can rest. The comet asks nothing of you. The mystery demands no immediate solution. The universe continues whether you sleep or wake. You have traveled far tonight, from Earth to the edges of the solar system, from present to past to future, from observation to speculation to mystery. You have earned your rest, your peace, your gentle drift into sleep. Let the last thought be not of answers, but of appreciation, for the comet that visited and departed, for the scientists who observed and recorded, for the universe that creates such wonders, for the consciousness that allows you to perceive and ponder them. We are blessed to live in a cosmos of such beauty and mystery, to have minds capable of wonder, to share this brief moment of awareness in the vast flow of time. The comet's whisper fades now into silence. Its journey continues in the darkness, patient and eternal, and you, having accompanied it in imagination as far as thought can go, can now release it to its path and yourself to rest. The mystery remains, beautiful and unsolved, a gentle question mark written in ice and starlight, a reminder that the universe is larger than our knowing, deeper than our understanding, more wonderful than our dreams. Sleep now, and perhaps dream of comets, of patient journeys through darkness, of returns and departures, of mysteries that need no solution. Dream of a universe that whispers rather than shouts, that reveals itself slowly to those who watch with patience, that saves its greatest wonders for those who can appreciate questions as much as answers. Dream of your place in this vast, beautiful, mysterious cosmos, small but significant, brief but meaningful, a conscious witness to wonders beyond imagination. The comet's story ends where it began, in darkness and silence and mystery. But the wonder it inspired continues, rippling outward like gravitational waves, touching minds across space and time, connecting us all in our shared curiosity about the cosmos. This is its true return, not in 12,000 years, but in every moment someone looks up at the night sky and wonders what might be out there, travelling in the darkness, carrying ancient secrets, following paths we can barely imagine. And so our contemplation comes to its gentle close, not with answers but with appreciation, not with certainty but with wonder, not with conclusions but with continued mystery. The comet has been our companion through this journey, and now we release it to continue its own journey, wherever that might lead. The question of its return remains open, a door left ajar to possibility, a window through which wonder can always enter. Rest now in the embrace of mystery, in the comfort of not knowing, in the peace of a universe that unfolds at its own pace, revealing its secrets slowly to those patient enough to wait, curious enough to wonder, and peaceful enough to accept that some questions are more beautiful unanswered. The cosmos continues its ancient dance, and you, for this brief moment, have been part of it, a wondering witness to wonders without end.